Okay. We have one item left in the deep learning stack. We still have to talk a bit about the basic workings of diffusion models to close that part off. And then we'll continue with the next chapters on supervised modeling and introduction of data science tools that will lead us going forward to more big data-oriented applications. First, as always, a bit of news articles. This is about a new paper that was pretty recently released. Deep learning is not so mysterious or different. Basically, it tries to provide an investigation why we have observed for over-parameterized models, like deep learning models typically are, where they can go beyond a regime of overfitting and basically return to a situation where they start to again decrease their validation loss. So that's especially something that people have observed with large language models, and people are trying to make sense why that happens. This paper basically argues that the answer lies in regularization, and it is not something that is specific to deep learning, but basically you can see happening with any sort of model that is over-parameterized and where you can include a soft preference for simpler solutions, which exactly what regularization is by adding that to the loss function. Now, the reason why we don't see it commonly and we only see it with deep learning models is because there you typically encounter those use cases where you can easily start with a model which is over-parameterized. The paper itself is pretty lengthy, but it's a very interesting one. It also makes some claims as, okay, so are there then things that make deep learning special compared to other machine learning approaches? And it basically investigates a couple of those. The fact that deep learning is well suited for representation learning, for instance, is different, or which is a bit special about these type of applications, that they are universal learning models, and it also provides an analysis of the loss landscape as well. We already had said previously that it's not so much the local minima that are a problem here, but typically these saddle points. So this paper also finds some interesting findings there. So check that out if you're interested. It's a pretty interesting one. Then some newer topics also have to do with new visions on large language models and how they can be utilized for recommendation systems. So obviously, just as with any type of model, you can probably also imagine that there is a possibility space here to utilize large language models as some kind of new approach compared to standard collaborative filtering or other recommender system approaches. So this article provides like an overview of what are the different approaches, how LLMs can be utilized in recommender systems, and which approaches work well for that purpose. There is also a link to an application which is called, or recommender system, which is called Beeformer. And also this is a relatively new one. And also here the authors utilize a large language model, but they use it on top of a traditional collaborative filtering approach to deal with the cold start problem. The cold start problem being that if you have a new user on Netflix and they haven't seen any movie yet, that it's hard for you to recommend them any movie too. So basically what is then typically done is that you try to recommend things based on descriptions of both the items that you want to recommend and the user that has just signed up. Maybe something about their profile or something like that. And this paper basically proposes to utilize an LLM to do that handling or to do that part, and they find that it works better than alternative approaches from the past. This is also something cool. This is something that Microsoft has just released called Data Formulator, and it's basically a business intelligence tool, you could call it, but also, as always, driven by a large language model where you can easily whip up data visualization, something that you would normally have to do by either coding in something like Matplotlib or Seaborn, or you would install like, or use something like Power BI, or you would utilize something like Tableau, these typical dashboarding and charting tools. Here it's basically completely language model driven, and it basically can come up with these kinds of visualizations out of the box. And it's free to use. You can open it up on Codespaces and play with it yourself. So also pretty fun. Then there has been also a new model released, which is also pretty impressive. This is something called Spatial LM. And we already had good vision models. Actually, we were talking about them last week, where they do some sort of segmentation or they draw bounding boxes around objects of interest. Well, this model is capable to do that basically whilst walking around in a 3D space. And the boxes in this case, they're truly three-dimensional bounding boxes, right? So they're not two-dimensional bounding boxes on top of the image. This has a spatial understanding of the full scene. So again, if you with baseline models like these, the applications that you can think of become again more fancy than what we could do in the past with simpler two-dimensional models. Also in the space of two-dimensional models, there has been kind of some new developments. I think maybe last time I already saw YOLO-E. This is another model, but this is still the more traditional two-dimensional approach. But also there people have been or continuing to work on models that are better at this sort of stuff. There's also star vector, which is also pretty interesting. So there the idea is to, let me try to find the right tab. Yep. Basically, this is a model where you can give it a image description, or an image rather, and rather than generating a description from that, or maybe converting it to a different style of image, this is a model that has been specifically trained to convert that image, which is a pixel image, a raster image, and generate the SVG code that you would need to generate something that matches that image. And that's then something that you can easily open up in Photoshop or any kind of vector editing tool and get started from there. So basically, you had older attempts that try to manually raster over the image and do it that way, or maybe you had to ask an artist to do that for you. Now you basically get a condensed representation in a vector format from a model. So again, pretty interesting and pretty useful. So if you need to reproduce like an image for your paper, for instance, and you want to have that as a vector image because then you can rescale that as large and small as you want, this model is doing a fantastic job at generating the SVG code for that. And then finally, and this is something not technical, but this is an experiment that was set up. So also this is a paper, more than 50 pages, so you can read through that yourself. But especially for those in the consultancy sector and those working in companies, and they were looking at all of these AI things and co-pilots and agents and so on, kind of thinking, where is this now going towards? Is this actually helping my employees or not helping? This is one study performed in one organization, a large organization. So this experiment or this study set up an experiment with more than 700 employees at Procter & Gamble, the very well-known global consumer packaged goods company. And they divided them into separate teams where, and that's what these, over some of these charts show, where people had to work on tasks as an individual, or people had to work on tasks as a team, and then both variants, both with any AI support or without AI support. And then kind of seeing what had the biggest impact. Is it like because people work in teams, does that make them happier? Does that make them perform better? Or if we give like an individual, an AI agent, what's the boost that we get there? This paper concludes that both having an AI and working in a team is the best outcome, but for many of the dimensions that they investigate, it seems to be better that if you need to make a choice that you would prefer giving an AI to the individual rather than giving them a team. And that's maybe a bit surprising. It's a strong kind of selling statement for AI tools, you could say, rather than for teams. And they test this on dimensions such as the quality that was produced by the work. So the worst is this individual that doesn't have any AI. Team does a bit better, right? But individual plus AI does even better than if you give them a team without AI, which is what the blue bar there shows. And they did not only look at kind of quality in output that was generated, but they also investigated the amount of positive emotions and negative emotions that the employees experienced whilst working on these tasks. And also here, they experience less negative emotions and more positive emotions if you give them an AI rather than if you give them a team. Strangely enough, if you give them both, then it's okay again. So there's also like an interesting interaction happening between these both cases. They come to lots of interesting conclusions. AI adoption at scale will reshape not only performance, but also expertise and social connectivity and how those manifest within teams. Fun that such studies are being done on already a pretty large scale. I mean, yes, it's one company, but 700 people, that's nothing to scoff at. So will be interesting to see further kind of studies like these are set up, and maybe when you can see differences depending on size of company or sectoral effects or maybe type of work that is being performed and so on. But this is a first nice step in that sort of analyses. Good. DAM. I think last time we were just starting to talk about DALL-E. We had taken a look at some StyleGAN examples. So we spoke about the generative adversarial networks, which we saw as an alternative to generate images that was quite popular for a time at least, where you have these two networks kind of fighting against each other. One is trying to do as good of a job as it can to generate fake images, and that discriminator try to detect it. And then whilst training them at the same time, you could basically have the generator learn how it can create believable instances from something noisy, from that latent space. We also saw an alternative approach, or a couple of alternative approaches. We spoke about the variational autoencoder, where we basically try to do the same thing, is that we could, from latent space, extract something that is then looking like a believable image coming from our data set. And then very early attempts where you can play around with the intermediate layers of something like a CNN, things like Deep Dream and style transfer, you could also regard as being generative approaches for images at least. And then the last, or the latest, what's still being done, kind of approach to tackle these generative questions, especially for the image domain, although these models are, the past weeks are seeing a bit of a revival in text as well, so we will see where that goes towards, but especially for the image domain, kind of what kickstarted the next improvement in terms of doing better at generating images was thanks to diffusion models. And there had been other approaches as well, like DALL-E, one of the very first releases that people said was actually quite good at image generation and was basically ready to be utilized in this setting. That one still made use of a transformer-based approach. We'll still need to look at the transformer, together with a variational autoencoder. And they set them up in tandem so that they could have the transformer kind of instruct or sample from the variational autoencoder to then generate the image from. And the transformer is also the thing that takes in the input text tokens, because also this model was already capable to listen to a prompt of a user. So that was also kind of the next step, that you could actually ask the model what you want to see. You do not need to have to collect a data set of images that look alike or look similar to the ones that you want to generate. You can just basically prompt the model, and to do that they popped a transformer model on top of this. Okay, that worked relatively well. Transformer is trained autoregressively, trying to predict future tokens, so image tokens coming from the VAE, all trained beforehand on a large collection of images. Now, what they already knew at OpenAI is that this approach probably would have its limitations and was not perfect, and they also felt that probably the generative adversarial networks, we have seen that those are hard to train, so they also knew that that was probably not going to be the solution anymore. So they started to experiment then with a different idea whilst working towards DALL-E 2. And what they experimented with, and that's then the other kind of approach how you can do generation from images, is by what we can call, or what is called, a diffusion-based approach. Related to flow models as well, but that's a little bit out of scope, so standard diffusion process. How does that work? Again, if we would not care about the prompting mechanism, that makes things a little bit harder to train, but we would just want to generate images again, like we have been doing previously from a collection of images that we have. We collect a whole bunch of cat pictures, for instance, in this case. And then gradually, step by step, we're going to create noisy versions of these images. So we're going to take a little bit of white noise, and we're just going to add that on top of the image that we have. And we generate a couple of variants of this. So for every original image, we can generate as many noisy or little bit more noisy versions as we want, right? And then for these little bit more noisy versions, we can continue that process, and we can add in a bit more noise, right? And we can, for every little bit noisy image that we have, we can generate an even more noisier bunch of images. And we can continue this process all the way through until after a couple of steps, you don't recognize anything in the original image anymore. And then basically, you just set up an architecture, and probably that will be using some sort of convolutions and deconvolutions again, probably something very similar to a UNet that we utilized for segmentation, where you take an image as the input. And with a segmentation model there, we asked, okay, for every pixel, predict me the class that this pixel belongs to. We could also train a model where we say, look, I give you this noisy image, and you need to predict what the noise is that I should remove to go back to this image. And that's basically what we try to teach this model. And of course, in the beginning, if you would calculate the loss on images where you start with something completely noisy, it's probably not going to do a very good job at those training samples. But if you give it images that are already quite close to the original, probably here it will learn how to do a good job to predict you, this is the noise that you should now remove from this image. And if you repeat this process on stepwise on trying to predict to go from here to here, and trying to predict to go from here to here, and predicting from there to there, then you'll have a model where, in fact, it is possible that you start with something that's completely noisy, again, a random sample from latent space, a random image, and you just ask your model a couple of steps. Please remove the noise from this thing. Please predict me what the noise is that I should remove from this image. And in the first step, that's almost going to be like some, random noise removal in essence, right? I mean, it's not going to see any objects yet in there, but basically what it does know is that all these noisy objects, they don't look like real images. Real images, they have more brighter spots and darker spots and edges and so on. So it will try to move towards something that already is a little bit more cleaned up, and maybe with some bright spots and dark spots. And then if you ask it again, it will basically hallucinate, but maybe this white spot, that could be the center of a cat. So I will also remove noise so that it starts getting a nose there, and it starts getting ears and fur. And so it basically distills or diffuses the noise away until you end up with a clear looking picture. So at inference also, these models are run over a couple of steps, right, to end up with a final generated image. That's pretty easy to set up if you, again, do not care really about a prompting mechanism. They're similar to GANs, that they produce an image coming from randomness, but GANs are hard to train, and generators can fall into mode collapse, so this approach works better. It turns out that this is the easier way to set a image generation model up like that. The next step then is obviously, okay, again, you will have to, or you would probably want to then train this thing on not just cat images, but on a whole bunch of images that you have coming or scraped from the internet. And also here too, there was still then the question of how do you add in an efficient prompting mechanism to this thing then? That's then your next step. So these architectures, you can use a UNet architecture, as already mentioned, with the same input and output shape, and basically you give it the input image and you have them learn what is the noise here on the output side that I should remove. We already saw that when we spoke about image segmentation. So how can the prompting mechanism added in? Well, basically, you have different ways to set that up, but if you think about it, during training at least, if we're asking to remove noise from this thing, and we do have a textual description of this image, right? That's a data issue. That means that we can't just collect a whole bunch of images, but we probably also need to have some textual description for these images. But okay, if you scrape the internet, images have captions, you're probably able to find that. But then during the training process, rather than just including in your loss, hey, you should be able to predict me what the noise is, right? You should also be removing noise in such a way that the image that you get closer and closer towards, that if I would, again, somehow be able to get a textual description for the image that you have generated, which not easy to do, but let's say that we could get a textual description for the image that you have generated, then I could compare the image that you have generated and the textual description that I actually saw in my example, and compare both. If they're the same, good for you. If they're not the same, I can include that somehow in your loss function as well. So what I need is some way to compare, is the image that you have generated, is this close to a given textual description? You could say, okay, maybe you can use another pre-trained model to do that, right? Maybe something like that exists. Indeed, that's exactly what OpenAI was also working on around the same time. So to guide that process, or to make sure that models generate things that look like textual descriptions that have been given, a prompt, right, in the case of image generation, they were working, or they utilized the concept that they call CLIP guidance. And CLIP is a model that they were building, and they had, in fact, simply collected a whole bunch of images coming from the internet with their captions. And then they first trained a separate model whose job it was to, and you can set again that up in different ways, but I think the way how they did it is they gave an image to the model, and then they gave a whole bunch of possible captions. And the job of the model was to learn which is the correct caption for this image. What is the right textual description for this image, right? And basically what you get out of there, once you have a model that you have trained and it is actually capable to do this, there you can utilize such model in a way where you can say, okay, given an image and given a textual caption, a description, how close do you think that these two are to one another? And that's then something that you can directly utilize in the loss to train your diffusion model with. So basically, it's indeed making use of a model that they already had pre-trained, and where they saw, hey, actually, this is a good strategy to kind of see whether an image is close to a textual description, yes or no, right? And that's exactly what you need to kind of train a generative model like this. So that's another, you could call that a self-supervised example of a model, because it's not that you come up with like a clear target beforehand. You just say, well, I have a bunch of images with their captions. What are some tasks that I can set up based on this to maybe improve downstream models, or maybe have models understand the relationship between text and images? Well, have them predict the right caption that belongs to an image. Probably over time they will get better and better, and then we can utilize that model in different ways, for instance here as a loss provider model. What is also cool is that you can then at least start doing some interesting things, but again, that would go a little bit into detail. But basically, we didn't see embeddings in detail yet, so that will come later. But basically what this model does is, if you want to compare how close is an image to a given caption, first you create embeddings out of these two things. So you basically embedding here, meaning you create a representation for them, meaning you create a vector of numbers that represents that image well, or that represents that piece of text well. And that's exactly the job of the model to figure out, is how to, given a piece of text, to create such a good representation, right? It's again comparable to what we actually wanted to do with our variational autoencoder, is to map all of our examples in an n-dimensional representational space, so that the representations are useful, that they make sense for the downstream task at hand. Similarly here, the downstream task at hand is given two vectors. I need to learn how to predict how close that these guys are, so I better try to do a good job to learn how I can map images and how I can map textual pieces into those two representational spaces that will make my downstream task easier. So next time, if we want to prompt an image, and we give it a textual prompt, and we say, well, I want to have a Van Gogh painting of a starry night, and then you get something out on the left-hand side, and on the right-hand side you say, I want a picture of two beautiful doggies, and you get a picture on the right-hand side. Internally, when you run that model, and when the model is generating or going through its diffusion process, again, we are going to take the image that the model is generating, we're going to map that to the representational space of this clip thing, we're going to take the text that the user gives, and we're also going to map that to get the textual embedding, and then we compare how both of them, or how close both of them are to one another. Now, that means that if we would skip kind of the prompting step and we would say, okay, what is then the vector representation for the prompt that the user has given here, and what is the vector representation for the prompt that the user has given there? Basically, you can then see, okay, if we interpolate between these two vectors, and we give that as kind of the text prompt, the text representation, to the diffusion model or to our generative model that we have here, again, you can kind of question whether the latent space then makes sense. Exactly the same thing as what we actually wanted from our variational autoencoder, is that you get some sort of gradient between your embedded points that you have made. Same here, you also see that you clearly get like a nice looking gradient, where indeed the model has the capability or has knowledge on how to create something that is in between or halfway in between a starry night of Van Gogh and a picture of two dogs sitting there. So it's nice that in terms of generative capability and learning how to represent objects, images in this case, together with textual elements in some kind of internal representational space, and that these models are capable to do this, it's quite nice, obviously, and this is what turns out to work well. So diffusion-based models are the ones that are the most popular ones nowadays. Also for video, this is quite common. In that case, they often get combined again with a transformer model as well, to kind of do the frame-by-frame generation or work on image patches or something like that. Now, the problem with DALL-E 2 is that it had good results, but it was not open source. So the community tries to then replicate these results, and those are then the models that have become known as stable diffusion. So stable diffusion, coming from Stability AI. Why stable? Because they add something else on top of this standard diffusion setup, where their goal is that they wanted to have these models run on commodity machines, on consumer GPUs, not to have a whole data center of them, but something that you could run with just one GPU. And that's difficult because if you take this setup and you need to diffuse a complete picture and you work with a UNet architecture, this thing is pretty heavy, especially if you like to generate pictures that are high in terms of resolution, right? That are large-sized pictures. That basically means that this input and this output, they increase in size, and basically the thing will blow up relatively rapidly. So what stable diffusion basically implemented is this concept of, okay, but maybe you are not, or it is not necessary that you apply this diffusion process where you learn how to remove noise. Maybe it's not necessary that you do that directly on pixel space. Maybe it's not necessary that you try to learn this directly on this full large-sized image that you have here. Maybe again, this is a process that you can learn separately on a smaller representation of this image that you have. And that's exactly what they do. So first, what they do is they will take the given image and they will take a powerful pre-trained autoencoder, again, to map that image to a lower dimensional representation. And then they add the noise and they learn how to remove the noise in this green part of the model on basically this lower dimensional representation. So it's basically diffusion, but now not applied to an image, but just to a vector representation of the image that you had. And then on the output side, once you have asked this thing has generated the noise in inference, you can basically ask the decoder part of this autoencoder part here to convert the representation back to an image for you. And this helps because this basically separates both the learning on how to compress images to make them work well in a lower dimensional representation from the process of learning how to generate these things by noise removal, by the process of diffusion. And it turns out that thanks to this dimensionality reduction approach, that you get something that indeed is capable to run on a consumer GPU. And today, those are most of the models that you see in generative imaging, at least. So most of these are heavily diffusion-based. People have been trying to make them even smaller. People have been trying to have this diffusion work with less steps, because in inference, if you start from a noisy image, but you need to run it through the model 50 times until you end up with something that looks clean, it takes a bit of time. So people have been trying to have the model learn how to remove more noise in a single step. So far, that also seems to be going quite well. As long as you scale up the architectures and you give it more data, that seems to be something that works. And the latest models, they have been trying to set up things like this, where they do not only generate images, but they also generate video. And then typically consistency is an issue. You don't want things to, a person change the color of their outfit from one frame to the other frame. So that's why typically there you need some attention mechanism. You need to put a transformer architecture on top of it to guide the generation of images from one frame to the next frame. That's a bit more heavy. That's not something that's going to run on commodity hardware, at least not at the moment. So that's why there haven't been a lot of open source capable video generation models that you can easily run. And those are mainly or mostly still commercial initiatives. Now, for assignment 2, you guys are working on this. Yeah, what to keep in mind, think about the basics. So tune your optimizer, your learning rate. So don't forget about those things. Also, don't forget to normalize your inputs, also for images, commonly made mistake. Try to use dropout, try to use layer normalization if you want to deal, or if you see that you're dealing with overfitting. Batch size, try to set that as high as possible, but that's typically not a hyperparameter that requires a lot of tuning. Just the higher the better, until your machine can't handle it anymore. Try to play with data augmentation. And in today's age, yeah, also use a pre-trained network whenever possible. Don't train everything from scratch all the time. That's not modern anymore. That takes way too long. You will probably not get results that are as good. So if you have a model that already does 90% of the task that you're facing, makes sense then to utilize that model instead. We will return to deep learning when we will talk about text. So I've already mentioned the transformer model a lot of times, and self-attention and embeddings and so on. But that's a topic for when we start talking about text mining. First, there is a bit going back to the more traditional setting, let's say, and talking a little bit about unsupervised learning. Here we'll talk about clustering, but quite rapidly, because clustering is not a new topic for most of you. But we'll see some clustering techniques that you might not have seen previously, and that are pretty interesting to use. And then we'll mainly talk about dimensionality reduction techniques. We already have seen one, in fact, when we spoke about the autoencoder and the variational autoencoder. Those are dimensionality reduction techniques, but we'll see a couple of other ones today as well. And then also some techniques for anomaly detection, which are pretty interesting as well, and something important to have in your tool belt when dealing with tasks in practice. So for supervised learning, there used to be association rule mining in there as well, but almost no one is using that anymore, so not that necessary to discuss. But you have more unsupervised techniques than just the ones that we discuss here. Contrary than supervised learning, now we are not really trying to say, okay, you have your features and you have your target, and the choice of the algorithm basically boils down to, they all do the same. Try to correlate your inputs to your output that you want to learn. The way how they do so, or their performance might be different, but the task for supervised learning is very often the same, right? It's basically try to map inputs to outputs. With unsupervised learning, the task will be very often oriented to, well, if it's purely unsupervised, you will see things such as, well, you're trying to summarize things, or you try to find patterns in your data. And so what type of technique that you utilize will kind of influence what type of patterns that you get out of there. For clustering, the pattern that you try to find is you want to make groups, or you want to find groups in your data set. If you would use association rule mining, then the type of patterns that you want to find, or if this and this and this shows up in the basket of a customer, for instance, what other elements are also likely to be in there? So then your pattern looks more like that. For dimensionality reduction, there the pattern that you want to find is, how can I create a low dimensional version of this data that I have that was perhaps to begin with very high dimensional? You have a question? Yeah, they are. You don't see those? No? Huh? That's annoying. Well, I will double check later. If you can't download them on Toledo, they should also be on sepa.net/AA. At least, I hope that they're there. And for today, yeah, so they should be here. No idea why they didn't show up on Toledo, but I will double check that later. Yeah, okay. Yeah, thanks for mentioning this. Where was I? Ah, yeah, unsupervised patterns. Basically, but again, there is an annoying word, and both supervised and unsupervised learning try to do this in a way. Every learning boils down to that the algorithm will try to find some sort of representation of your data that you have, and a representation that works well for the downstream task. So if you think about supervised approaches there, that representation, this wrangling that we had for deep learning, for instance, at the end of the day, it tries to hunt for a representation or tries to learn a representation of your data where the classes become nicely separable. For unsupervised learning, because there you don't have classes, the question there is then, okay, what does it mean to think about some good underlying representation of your data? And when you think about dimensionality reduction, and if you consider a technique such as PCA, for instance, there it is well known, okay, you would like to retain as much of the variation in your data that you had in your original feature space in that reduced feature space. So probably there, a good representation for each data point will boil down to how can we ensure that two elements that are far away from one another in the original feature space are still far away from each other in the reduced feature space. So for dimensionality reduction, we could kind of think about representations being good from that perspective. If you think about clustering, there it will be probably something distance-based or similarity-based, which is also something that you see very often in the case for unsupervised techniques, that they will adopt some notion of similarity, distance that they want to retain or work with, or frequency as well. Might not always be that that's the pattern that you want to find. Sometimes you want to see the infrequent patterns rather than the frequent ones. So hence why we'll also talk a little bit about anomaly detection as well. Because very often you're more interested in hunting for the things that are more hidden rather than the things that are common and you probably already know about. So clustering, yeah, there the task is relatively easy. You try to group objects together in clusters, in groups, in such a way, and hence what does it mean for such a grouping to work well? Typically in such a way that if you then take instances that fall in the same group, that they are similar to each other in some way, right? So there the question will be, you will probably have to provide some notion of similarity or provide some notion of distance that we can use to quantify our clustering result in terms of are members of the same group or these similar to one another. And if we would take members that do not fall in the same group, so across the groups, there you probably want to have them as dissimilar as possible to one another. So clustering is utilized for basic data analyses, things such as customer segmentation and stuff like that, but is also sometimes used as a pre-processing technique. It can be utilized, or when we looked at the interpretability technique LIME, and also in the case of Shapley values, you could do that. Their clustering was applied directly on the image to create these groups of pixels that were then hidden out. So shows up in a lot of cases. Now, if I would ask you, why are there so many different clustering algorithms then, if the goal is generally kind of the same, right? Is of course, again, because they make different trade-offs in terms of what they consider to be valid groupings and how they work with the distance metric and so on. So here are 4 techniques. Yeah, 3 solutions on 3 data sets for each of the 4 techniques. The first one should be pretty recognizable, right? But if I look at purely subjectively speaking, and this is what makes it so that you have a lot of choices here, obviously, what is your preferred choice amongst these 4 techniques? Probably you will say, well, not the first one, in fact, because here I see that the line gets cut off, right? And suddenly we go into another cluster, and I would rather prefer to see something like this one, where the 2 kind of lines are in their own cluster with one another. And similarly for the bottom port, particularly don't really like this outcome. Maybe this makes more sense from a human perspective or from a visual perspective looking at this. And for the top row, it also kind of makes sense that we have 3 blobs here of data points, so we would expect to see 3 clusters over there as well, right? But that's simply because that's our human subjective notion, right? That's point 1. We have a certain way to look at things, and we tend not to just look at closeness, which is something that the first technique is heavily focusing on. We also tend to look at things such as continuity, right? Which is why that we believe that these or this data set forms two clusters rather than one cluster looking like the top part and one cluster looking like the bottom part. So they're like psychological notions in the way how we look at the world that cause that certain solutions look more appealing to us than others, but that doesn't mean that that is necessarily the best solution for any downstream task that you might have. Secondly, all of these examples are always easy to reason about and to kind of see, well, the solution makes sense to me, yes or no. But that is, of course, because all of these examples are typically two-dimensional, where you just have two features, and we cluster on these two features, the x and y coordinates in this case, whereas we work with data that, of course, has more than two features, right? And then even just visualizing the clustering solution might not be as easy. So we probably also will need to look at some ways to tackle that aspect as well. Another way how these clustering techniques differ is whether they go for a hierarchical approach or they go for a partitional approach. And the hierarchical approach, as the name suggests, will not just end up with giving you a clustering solution, but it will also give you like the full lineage how it came to that clustering solution. In other words, you can think of it going from both sides. I could say, well, at the limit, I could consider that all of my data instances, so every instance, that all of those are in their own little single cluster. That's the most unclustered solution that you could start from. And then the hierarchical aspect that comes into play will, of course, be that step by step, I can decide which of the two existing clusters to merge with one another, until you end up with the other limit where you have put everybody in a single large cluster. So that could be the other kind of approach that you could take hierarchically, is that you consider by saying everybody is in one huge group, and I will try to step by step split up one of the existing groups into two pieces. And then you also create like a hierarchy that you can go through. So some techniques work like this, and then you do not need to decide up front how many clusters that you exactly want, because you get the full hierarchy, and then the decision of how many clusters that you want to end up with is basically where you position yourself in that hierarchy. A partitional approach does not create a hierarchy. A partitional approach just says, okay, very often it will ask to give the number of clusters up front, not always, but quite often, like that's exactly what k-means does. It asks you the number of clusters that you want, and it will simply say, here is the solution. But there is no hierarchy to move through or to navigate through. You just have that clustering solution. So here are the two approaches that we could take with hierarchical clustering, basically by considering that everyone is in their own single cluster, and then we try to merge these groups and bringing them together until you end up with everybody in there in a single large cluster. So that is called agglomerative clustering, because you agglomerate the clusters together. And going from right to left, that would be the alternative approach. That would then be called a divisive approach, because you start with everybody being in their own, everybody being in a single large group, and we kind of need to decide, okay, which of the groups am I going to split? And secondarily, how will I split the groups, right? So with divisive clustering, there are two questions that you need to figure out. Which of the existing groups will I split up? And once that I have chosen one, how will I split it up, right? Because there are different ways how you could make a cut in these 5 members, right, rather than just a single solution that's being shown here, right? I could also have put C1 and C5 into a single group and kept the rest separate as well. So that's a question that you need to answer there. When you go agglomeratively, the only question that you need to figure out is which of the two or which two existing groups will I merge with one another? There is no how will I merge them. No, you just slap them together, right? You add them together. So there you could say, well, maybe the realm of decisions that you need to figure out is smaller for the agglomerative case than for the divisive case, which is probably a benefit. Again, what does it mean for two existing groups or two existing instances to be similar to one another? Well, this is in fact where the whole kind of distance question comes into play, right? This is why this is so subjective. On the one part, is because there is a lot of freedom that you can take in terms of which distance metric are we going to utilize. When we consider, for an instance, that we will work agglomeratively, and we consider that we're not working on images, although you could perfectly figure out a distance metric between images as well. In fact, if you think back to what we have been doing with these deep dream kind of applications, where we basically utilized our model to kind of give an indication how close an image is to the style of a certain other image, for instance. That's something that we actually could use as a distance metric as well, and use this to set up a clustering run over a bunch of images, for instance. You might think about applications where you are clustering text with images together, and then maybe something like a clip loss could be utilized there as some distance metric. So it doesn't necessarily need to be a vector of numbers. Basically anything that you can specify some measure of similarity for could be something that you can cluster, obviously. Now, let's say that we work agglomeratively, and let's say that these are just customers with their features, so all of my instances C1 to C5 are just feature vectors. In the beginning, at this very first step, actually there the question is a little bit easier than in step number 1 and 2 and so far. Because in the very first step, I'm just trying to figure out which two instances that I have are most similar to one another, right? If I'm comparing two instances, then I need a distance metric that gives me the distance between two instances. So that's what you need to specify for me. Like I give you two instances, you give me a value that indicates their distance or similarity, right? Once we are a bit further in this process, we actually need to add in something additional as well, because then, in the case where we end up at this step, for instance, we still have a single instance, right, the C3, which gets merged in with this cluster. But here I need to have a mechanism to not just calculate the distance or the similarity between two instances, but between two clusters that have multiple instances. So that's another thing that I will have to figure out if I want to work hierarchically in this manner. But we can start easy, and we could think, okay, in terms of providing a distance metric between two instances, there are your common easy choices, Euclidean distance, Manhattan distance, squared Euclidean distance, maximum distance. There are many more possible choices that you can find. Cosine distance, if you have it's typically a commonly utilized one if you have a high dimensional vector that you're trying to calculate the similarity for. If you have vectors that consist only of binary values, something being present or something not being present, a 0 or a 1, then you could use something like the Jacquard index or other kind of comparative metrics to calculate the distance for you. So it depends a little bit on the data that you're working with and what you hope to see or where you want to drive your clustering results to. If you're working on clustering locations on a map, then maybe Euclidean distance does not always make sense. Maybe it's better to use the distance in terms of travel time instead, right? Because it could be that it's a very heavy road and two things that are close to one another spatially might not be easy to reach, so maybe you do not want to put them in the same cluster. If your clustering task is about which locations are kind of in the same area, driving around, but not necessarily like in the same area, looking top down at the map, so then you would utilize such kind of distance metric instead. So there are many of these that you could pick. A good distance metric typically possesses some evident properties, like if you would take the distance between two instances A and B, that is the same distance between B and A, right? It wouldn't make sense. You could think about applications where that is different. For instance, for travel time, you could say, well, maybe in some cases, if it's like a certain time of the day, it's easier to go from A to B than it is from B to A. So it's not necessarily the case that you always should possess these properties, but sometimes techniques will complain if your distance metric does not have these properties. But there is no fundamental reason why sometimes you wouldn't be able to play around with some of those at least. What is also very often the case, and that's even a more stricter one, I would say, for techniques, is that if you compare yourself to yourself, your distance is 0. You're perfectly similar, right? I think that makes sense. Distance metrics should be positive, but if they're not, you could just add a constant to them to make them positive, so typically that's not a big deal. And also the triangular inequality should hold, meaning that the distance to go from a point A to B should always be smaller than if I would travel through some third intermediate point somewhere else, right? If I added an extra stop going from A to B, I expect my total length to become larger, never to become smaller, right? So that's also a typical property that these distance metrics should have. This solves the mechanism of how we can calculate the distance between two instances, but we still, of course, need to tackle the problem of how do we then calculate the distance between two groups, between two clusters. And this then, in the case of hierarchical clustering, is called the linkage criterion. So that's another thing that you need to specify, where you can play with different settings as well. And you could say, well, a simple solution is to calculate the distance between two clusters. First, calculate the basic distance that we already have between all pairs of instances, between cluster A and cluster B, and then just keep the lowest one as the representation or as the distance between those clusters. You can use this, but what you will typically find is in that case you get longer, skinnier looking clusters. You could also say, well, we keep the maximum distance. This leads more to tight clusters. Of course, what do most defaults end up doing, especially in the case where you're already calculating all of these pairwise distances anyway, to then choose the minimum one or the maximum one, is simply to average them, obviously, right? And that's typically the one that is more favorable, because this one is also more robust to noise. In case where you want to avoid doing the work of having to calculate all of these pairwise distances, because that can take up time, obviously, is that you say instead, well, if it's possible, but that might not always be possible, but if it is possible to define some sort of center point amongst the points that you already have in a cluster, then instead of calculating the distances between all these instances or pairs of instances separately, simply calculate the distance between the centroids of these clusters and use that as your distance between the clusters. But this means that you need to be able to come up with what such a centroid is. For numerical data, it makes sense that you can just take the interpolated value and find out the center of mass, and that's then your center point. But let's say again that my instances are not vectors of numbers, but they are textual things, or they are images that I'm clustering. For 5 images, probably it's not very meaningful to construct something like the average image or the center image between them, right? I'm going to end up with a gray-looking blur anyway, so my distances that I would calculate between 2 gray blurs would not be very informative in that case. So there you probably would prefer to use average linkage instead. There is also Ward linkage, which is similar to using ANOVA. The distance between 2 clusters is the increase in the error of the sum of squares after you merge the 2 clusters into a single cluster. So here you base it on the sum of squared errors. And again, then the question is, okay, but as a z, that's kind of some loss that we come up with now, that we include there. So what kind of loss, what kind of as a z are we actually calculating? Very similar to, as we could, or this is very comparable to basically what a regression tree was doing for us, where we always said, well, you start with the root node, and at the basic situation, if you would ask what is the prediction of that root node when you didn't make any splits yet, there we said, well, you take all the target values that you observed during training, you average those values, and that's your base prediction. And then to calculate something like your SSE, well, you run your instances and you compare their true values with that predicted value that you have. Similarly here, if you have a cluster, or you have 2 clusters in this case, and you're considering whether it makes sense to merge them, this thing says, well, you first need to calculate separately the SSE for cluster 1 and cluster 2. That means that you need to compare true values, but what are true values here? We don't have targets because we're unsupervised, right? So what is kind of the predicted value and the true value in here? Well, it's again based on this idea of distance that you have defined. And basically, this cluster says, well, again, if I would have to make a prediction, and again, it's easy because we only have an X and a Y feature, so that's why you can draw this position here, right? But basically, my centroid is over here. So then what I can do to calculate the SSE is I calculate the distance between every point and that centroid point using the distance metric that you have defined, right? And I square that distance and I sum that distance, and then I get my SSE value for cluster A. And then I do the same thing for cluster B, and then you get your SSE value for cluster B. And what will happen is the smaller that I keep my clusters, remember, agglomeratively, I'm starting from the idea that every instance is contained in its own cluster. So there, effectively, the SSE for all of my clusters that I have is 0, obviously, because they are right at their center point, right? So what this thing is considering is, okay, I do have to make a merge. If I put these 2 together, yeah, then the center point moves to here. My SSE will increase, right? So probably I will perform the merge that at least decreases the SSE, right, the least, and I utilize that. So I do have to merge. I know that my SSE will probably decrease by this merging process, but I try to keep it under control by picking at least then the best merge that is possible again. Again, also for this SSE thing, this requires that you can define the concept of what a centroid looks like. So this is for numerical data. If you would have textual instances or image instances or whatever, something that mixes categorical and stuff together, probably this is going to be harder, right? And then again, the only option that you kind of have is to use the average linkage instead. That's kind of the leanest one because it only requires the fact that you can that you have a distance between 2 instances, and that's it, nothing else. At the end, you get a hierarchy then, as already mentioned, because you start either by everybody being in its own cluster and you splitting them up, or you start at the bottom and you add them together, you merge them step by step together. So So with this, there is no need to specify your desired amount of clusters beforehand. You can just kind of slide over this hierarchy and then see how many clusters that you want. You can zoom in and zoom out of this solution. Drawback is, this is of course slow. If you have a whole bunch of instances, then you're merging all of them and merging the clusters together, so this hierarchical kind of approach can take some time to figure out the full hierarchy, so it's not very scalable. Also, because you work greedily, you only merge or you only divide, you never retrace your steps. Again, here you can theoretically have the problem that you end up in some kind of local optimum, and that the cluster solution that you find is not necessarily the best one. The best one, if you would then again position yourself somewhere in this hierarchy where you have 5 clusters, is, or those 5 clusters, if I then calculate the SSE for these 5 clusters in the way that we just did, does it then mean that I have a guarantee for the lowest SSE for those 5 clusters, or does there exist a potential other solution that has 5 clusters with a lower SSE? This says, well, it's greedy, so potentially there exists a better solution with only 5 clusters with a lower SSE. Just like a decision tree also didn't retrace on its steps, but there we saw that it was not really a problem. Very likely here it's also not very large of a problem. Also important is with these distance metrics, but I mean that's pretty reasonable, is that you normalize your features first, or you standardize them in some way so that they work on the same scale. Otherwise, of course, the impact that a certain feature has on distance might be way larger or way smaller than that of a different feature. So this is our what's called then our dendrogram with 2 R's, right? So then if we decide upon a cut, this is how we decide upon the number of clusters that we will get. In this case, we have 4 clusters, the purple one, the red one, the turquoise one, and the green one. But you can basically zoom in and out of this thing. Also nice, but it depends a little bit on your dimensionality of your feature space, but especially in cases where you work with toy examples with 2 dimensions, such a dendrogram can, not always will, but can also already give you like a look, if you inspect it visually, of potential outliers or anomalies. And what are those? Well, in the case as this point here, which is far away, basically in our stepwise merging process, of course, we have to wait until the very end, until it is decided that this point gets merged to the 2 other clusters that are then also still there. So for those points where it takes a long time before they get merged in with another cluster, those are typically like outlying points. And that can be on the level of a specific point, but that could also be already, maybe there are 3 points which are very close here next to each other, so those 3 points would be merged in quite quickly, but then we would see that that cluster stays on its own for the remainder of the hierarchy, or for a long time in that hierarchical overview. So this can be already some indication of where are my anomalies, where are my outliers, but we'll see more clever techniques in a second. So then the only thing is also, okay, if you work agglomeratively or divisive, do you end up with different solutions? Well, yeah, potentially, that can certainly happen. Also kind of an issue is that if you look at these linkage criteria, is that we always said, well, in this case, we will merge the 2 clusters that are closest to one another, and here we do kind of the same thing, but based on the centroids. And in the case of Ward's linkage, we kind of look at the increase of the sum of squares after merging the 2 clusters. So all of these linkage criteria ideas, they seem to assume that you're going to work agglomeratively, because they always talk about you're going to merge. You're going to start from the situation where everybody's in their own cluster and you merge up to the top part. So does this work if you want to work divisively? No, right? Here you just basically, again, do a pairwise comparison of clusters that you already have to find the ones that are closest to each other. But if you would work divisively, then of course this would fail to work, right? In that case, yeah, you start with a situation where you only have 1 cluster. A divisive algorithm would probably look something like, for every cluster that you already have, and for every potential ways that you can break it up into 2 pieces, prefer the one that most heavily reduces the SSE then, I guess, is something that you could utilize. But you can already feel that over time you probably will have to run way more checks, because not only do you need to check this for every cluster that you have, but also all the possible ways that you can merge this thing or split this thing up into 2 pieces, which will be way more than running pairwise distances that the agglomerative algorithm does. So to put simply, at least for like traditional cases where you just cluster based on images or features or whatever, all the algorithms that you will find and all the things that you will utilize implement agglomerative clustering. Divisive clustering is simply not utilized because it's too computationally expensive and not worth it to do that. There are some exceptions to this rule, and the exceptions will come once we will start talking about community mining techniques, which is basically, you could call it clustering for graphs. That there are some techniques that take a bit of a divisive approach, because with a graph, you already start with something that's connected, and indeed there the question could be is how do I split up this thing into multiple pieces to create my groups? So there we will see divisive applications, but also there we will see that those are typically the more slower approaches as well. So that will at least stay. Working divisively tends to be rather slow. So that's a hierarchical technique. And basically, for any sort of instance that you have, as long as you can come up with a distance metric, you can basically then create a clustering solution. So that's kind of a benefit of this hierarchical approach, that in that sense is pretty flexible. Partitional clustering then, well, here the most famous technique is obviously k-means, right? With k-means, you specify a value for k, how many clusters do you want? And again, let's say that we use our two-dimensional playing field here, so we only have two features to make the toy example reasonable. We start with a positioning of these k-centers that we will create. So again, here k-means is based on the concept that you can define what a centroid means, right? So again, for textual data and so on, k-means will probably give, either you find a way to featureize your text elements and you cluster on that, but otherwise, that's not gonna work. You decide random starting spots or positions for these k-centers. And then basically what you do is, in step 3, so I have a bunch of instances, let's say these guys again, and I have two clusters that I want to make, and I put one randomly here and one randomly there. And then step 3 is I perform an assignment. And I will say, okay, based on the distance between the instances and the cluster centroids as they currently are, I will assign you to the closest one. So you belong to this one, you belong to this one, you guys belong to this one, and all of you are closer to this centroid. But now you can see, well, based on this assignment, my cluster centroids are actually not in the right place, and I need to recalculate their position. So I move my cluster centroids to be actually in the center of the assignments that I have now done. But because I moved my cluster centroids, some of my assignments might have changed. So I recalculate, if necessary, my assignments. But because I did that, and maybe some of the assignments might have changed, I will have to recalculate the positions of my centroids again. And this process continues until you run out of time or convergence is reached. And convergence basically means that none of the assignments change anymore, right? Or maybe only very few assignments change, or maybe you, after 10,000 iterations, you give up and you stop waiting for the thing, right? But typically this will converge relatively well to a stable solution. So you repeat these steps until none of the objects change cluster membership. What k-means ends up doing is something very similar as what we just saw, is that by moving these centroids around and calculating assignments, it basically trying to optimize for a high intra-cluster similarity by optimizing towards a minimal total distortion. So again, it's trying to minimize all of the SSEs, or it's trying to minimize the SSEs for the clusters that it's positioning, right? For k going from 1 to the number of clusters, and then for every instance, based on the distance between that instance and the cluster centroid, which is this mu thing over there, you square that, and basically k-means is trying to optimize for this. So it's basically, the interesting part about this is that it's basically not optimizing at all, or it has also no notion at all of trying to maximize the inter-cluster distance. So the distance between clusters is just trying to minimize the within cluster distances by trying to keep points as close as possible to their centroids. This is also not an exact optimization. This is an iterative technique. So again, it's not because you have a bunch of data points on a map and you ask k-means, please find me the solution with 3 clusters, that you get the best solution by calculating this SSE approach, that is the best solution necessarily. Again, because this is a heuristic approach, not necessarily the globally best one. Except in the case where you work with one-dimensional data, then it is also the optimal solution that you get. And we have already seen in the very first week that in that case of one-dimensional data, that is something that you could apply, for instance, to categorize a continuous feature, for instance. Strength, this is very easy and very simple to implement. It has a nice intuitive objective function, optimizes intra-cluster similarity, and it's quite efficient. It's only, or drawbacks about it is, okay, but what if you cannot really calculate what a centroid is between points? Again, that same problem as before. So yeah, if you have categorical data, I guess you can create dummy variables for it first, or you can maybe find a representation, but this will not work on any sort of data that you want to cluster. You do need to have some kind of centroid for it. Also, what is important here, but most implementations do this, even although they will not mention it specifically, or like something about scikit-learn does, is it just calls it k-means, but it actually adds on a couple of additional kind of extras to it. What people quickly found out with k-means is that it often terminates at a local optimum, and meaning that if you restart the technique a couple of times, you can end up with solutions that are quite different, right? With a different SSE behind it. Because depending on your starting values, depending on your initialization, depending on where you put these centroids in the very first step, this can heavily impact the quality of your ending solution that you get. Okay, if that's a problem that you face, I mean, in deep learning, we didn't like to do this because there it was way too cumbersome, although for smaller models, it's also something that people typically did there. In the case of k-means, it's efficient enough. Every time you see that you're quite sensitive to some starting or some initialization positioning, just restart a couple of times and continue with the solution that reached the best SSE result. And most implementations will actually do that behind the scenes, that restart and try those multiple restarts. There is also an adaptation of k-means, which is called k-means++, but again, now is typically implemented in the same implementation without giving it a specific name anymore because it's so common. K-means++ says, well, instead of completely picking these starting positions for your centroids at random, at least try to have them a bit spread out in your feature space. And after picking your first centroid, which is something that you have to do completely at random, but to pick your second centroid, probably it will not be ideal that you put that one very close to one that you already have. So weight that sampling a little bit more so that places that are further away from centroids that you already have placed get a higher chance to be chosen. And you try to spread out that way the positioning of those initial centroids a bit. That also helps. So that's k-means++. That's the only change that it makes. That's also what most implementations do. Normalization will be required depending on the distance metric that you choose, but typically that will be something that you have to do. Also annoying is that this technique is sensitive to noisy data. This one is sensitive to outliers, because outliers, which are very far away from centroids that you're placing, they will heavily pull the centroids towards them, right? So this can heavily also impact what your clustering solution looks like. So if you do have noisy points and you plan to utilize something like k-means, you will have to deal with that first. A drawback is also that you need to specify the number of clusters in advance, but you could just try the technique with different values for k and then plotting the SSE values depending on different clusters that you have. And this can basically inform you a number for k. And this can basically inform you, I think there is even a picture, I don't have to draw it, yeah, your best cluster value. So for very low values for k, remember that's in the limited situation where you only have one large cluster, probably your SSE is going to be at its worst. And then if you increase the number of clusters, your SSE will improve. And in the other limit, you're putting everybody in their own little cluster. Probably there the SSE will reach 0. And then typically people pick like the elbow point as like a good value to use for the number of clusters there. Also, drawback is, so the situation on the right-hand side here, where you end up with a cluster solution where you kind of go, okay, you have put these 3 centroids there, but that's totally illogical. This is such a local minima with still a bad SSE value. Obviously, there is a way better solution, which is to put one centroid here, and one centroid there. Right? But here, k-means got stuck in this situation. There are no movements that you can do anymore on these centroids, and hence there are also no reassignments that happen here. So this is what you should avoid by restarting or by using k-means++. Another issue is that you will end up with clusters that look convex, that look round. Right? That's the only thing that they can do. Their assignment is based on distance, so you will end up with convex clusters in your feature space. In the 2-dimensional case, that looks a bit like circles. You could say, well, maybe you could think of some sort of weird distance measure that avoids this issue, but that's not going to be very easy, right? Because which distance metric could you think of that avoids this convexity problem by doing this kind of assignment? You could even think about first having an alternative representation of your instances, and then maybe you come close to inspirations from support vector machines, where you first map your points into some other space, and then if you map them back, that you get non-convex shapes, but that's also not very frequently applied for k-means. There is an easier solution, in fact. This is the main reason also why people will say that in practice they don't like to utilize k-means. And everybody, when they start working and they do some mini customer segmentation analysis for an organization, for a company, the first thing that they will say is, well, in university, everybody had to learn about k-means, but no one uses it in practice because, well, in practice it simply doesn't work. And what ends up happening are situations like on the left-hand side. This is data that, so this, I will say something about this in a second, but this is data which has features about customers. And you know that for your marketing analysis or for your segmentation modeling, you say, well, I already want to, we already work with 3 segments, which is our bronze, silver, and gold customers, for instance. So now I want to run a clustering on my customer base. So I'm also going to pick k equals 3 for my value or for my number of clusters that I expect to see. It's already a bit weird that if you already have 3 well-defined segments, why would you then still do a clustering yourself? But okay, there might be some reason, and maybe you hope to create your own clustering based on the features that you have, but then at least you hope to see that you find a cluster that has maybe the larger amount of, gold customers, and then maybe the other one has the highest amount of silver customers, and then the other one has the highest amount of bronze customers. And maybe those are the 3 groups that you try to identify in this based on the features that you have seen here. Okay, fine, you run this clustering solution. Bad result, obviously. Like, has placed these 2 groups into a single large cluster with obviously a bad SSE result. And also, if you would then try to inspect what are the bronze, silver, and gold customer distributions in these 3 clusters, well, here it's not gonna look good because it has basically mixed a whole bunch of silver customers with gold customers, so that's gonna be 50-50, kind of like a weird cluster. Here it's kind of okay, but also the cluster solution itself is not very appealing here either. What is typically way better is to not be too swayed by some predefined notion of, at the end when my analysis is done, I would like to end up with 3 clusters or with k clusters. And also not to be too afraid to set the value for k a bit higher than what you believe is necessary, right? This will also allow you to hunt for shapes that are not necessarily convex anymore. In the situation of these 2 lines crossing, the way how we can kind of show that, but you can think a bit about, okay, how many clusters are going to be necessary in that case? So if I pick 2, because that's my, for some notion, I believe that 2 is a good, or is my desired clustering result, which is true, right? We can see here that with 2 groups, this data would probably be fitted pretty nicely. But in this case, k-means doesn't do what we expect it to do because of that convexity problem. So what if I would increase drastically the value for k instead? Well, it would make a group here, with the centroid here. And yes, you get way more clusters, but then at least there is still the opportunity for you to again work a little bit agglomeratively afterwards, and by inspecting the different clusters, right, maybe you regrouping them or merging them a bit further, right? And then you can end up with something that can deal with non-convex shapes. And in the case of this customer segmentation, what the underlying problem is that you might already here have, yeah, based on your customer segmentation, you have your silver customers, but at least for the features here, there are clearly 2 different groups of silver customers. There is this group here at the top, and there is this group here at the bottom. There is no single group of silver customers, and more so, this group of silver customers is very close, at least based on these features, to your gold customers. So again, way easier to just say increase the number for k a little bit first, right? You will get something that maps better with the actual data, and then you can still inspect in these clusters, and then this will allow you to go strange. Here I have a cluster where there is a large amount of silver customers. Here there is also a cluster with a large amount of silver customers. These are 2 distinct types of silver customers. Based on that, you can then change to or decide to work with 5 customer segments going forward because you find that there is a better mapping on what's actually going on. That's a choice that you can still make, but at least you could then say, well, I maybe have two types of silver customers. It's better to put them in their own group. So long story short, don't be afraid to increase the value for k if you're working with k-means. But yeah, this comes at a price where you will have to do some manual analyses of the clusters that you get. But that's typically the case when you work with clustering techniques. It's rarely the case that you will just plot them on a map like this and go, oh, now I understand everything. That's only in toy examples that this works. Speaking, or now that we hear anyway, you notice that this says PC1 and PC2 on these axes. So this here is a data set where we originally had more than 2 features, right? And then the question is, what's the best thing to do here? Is it best to first do a dimensionality reduction to, in the case here, 2 dimensions, and then run your clustering on these 2 dimensions? Or is it better to first run your clustering on the original feature space, but then obviously to visualize this, if you want to create a map out of this, you do need to have 2 dimensions, right? And then apply the PCA, but simply to visualize the cluster results. Both are viable, but generally what people will prefer to do is to first run the clustering on the original feature space and then think about how to reduce the dimensions to visualize the solutions, because you do not perhaps necessarily have to visualize the solutions. That also means that your cluster boundaries might not always look perfect because you're looking at them after having reduced the dimensionality of your feature space, right? Whereas your clustering was performed on the original feature space that probably had more than 2 features in it. What else could you do? Yeah, visualize or inspecting the clusters based on what is commonly done is their centroids, for instance, which is like a good summarizing description of the average cluster member, you could say. But you can also inspect distributions over the features. Like here we did that we looked at what type of customer are you bronze, silver, or gold? But you could also use other features that you have, like we could also have done this for the age feature of our customer, and then maybe we could have seen that in cluster number 1, the age is centered around 70 years old, and cluster number 2, the age is centered around 50 years old, right? And do inspections that way. So typically a post hoc step after running something like k-means is to do manual inspections like those. This I already mentioned, this is how k-means ++ works, basically spreading the clusters out from each other. Now, if you still don't like k-means, and there are cases when you will not like it, and what is still an issue is in the case where you would have noisy points, for instance, or outliers, it's not going to work that well. And if you do not really want to remove them, you have some other options available as well. And one option which is quite popular and people tend to use even a bit more nowadays than something like k-means is dbScan. Stands for density-based spatial clustering of applications with noise. And the idea here is you do need to set a couple more hyperparameters than just the value for k. In fact, here you do not get to set an exact value for k. The algorithm will construct the clusters for you, and you don't get to choose which exact number of clusters that you want. And basically how it works is it decides to, in the beginning, it decides to start from a randomly chosen point. Let's say this red one in the middle. And it says as long as in a defined neighborhood around me, so that's basically where the distance also comes into play because it uses the distance to measure a neighborhood around it. If I have more than enough points in that neighborhood, I'm going to grab you with me in my cluster, so I'm also going to make you red. And then I'm going to spread out to these points and ask the same question. Do you guys still have sufficient points in your neighborhood as well? And this process continues until you come to some border point where you do not have sufficient neighbors anymore in your neighborhood. And then you say, okay, the cluster of these points, all of them belong in the same cluster, but I stop for this cluster. And then to continue forward, I will pick another point that I have not clustered already, and I will do the same kind of spreading mechanism there as well. At the end, there will be points for which if you start with them, like the blue point over here, that they immediately do not have any sufficient neighbors in their neighborhood to cluster them with any others together. So these are left out, they are not being clustered at all, and they're just being considered to be noise points. So the benefit with something like dbScan is that not only do you get your cluster solution, it also gives you an indication of what noisy points, or what it believes noisy points to be, which is another interesting way how you can hunt for anomalies, how you can hunt for outliers, is by using dbScan and looking at the noisy points. There is a nice, or you can see this in practice, how it works, a bit more visual than, let's say we use the smiley face example. We need to set basically the epsilon value, which indicates the neighborhood size and how many points we need to have in each neighborhood. I'm just going to leave that at the default values. Starts with this point, it's spreading out, and it's continuing to do so until it will reach one of these border points, and then says stop. Benefit here, also not the issue of convexity anymore. So this is able to cluster into non-convex kind of patterns as well, right? So this is something that we wouldn't be able to do with k-means. I'm going to let it run for a bit further so that you can kind of see the second cluster from being constructed. So there it's kind of bumping because the neighborhood is not large again. It's not large enough, but the other side can still continue forward. Probably it will also bump there. No, nice outcome. But then, of course, it has to continue for the two eyes. So it puts those in new clusters, puts the mouth into a new cluster. Likely there aren't going to be any noisy points here unless, no. So all of them in this case end up being clustered. If we change the hyperparameters a bit, no, I'm not going to take this one. Maybe this is better. We would make the neighborhood too small. There you can see, of course, at the top it's still able to figure out and to spread because the points are close enough to one another, but you will end up with way more points at the end that will be considered to be noise points in this case. So here you do need to tune those parameters a little bit, which is a bit of a drawback of this technique, but the solutions that you can get out of here are typically of a better quality than what you would get with something like k-means. Also not centroid based, which is also a benefit. So also here only this requires the notion of a distance metric being available. That's the only thing that you need to calculate that neighborhood and the number of points in that neighborhood. You do not need to come up with some kind of idea of a centroid for this thing to work. So here we have all these white points or noisy points. There are also other techniques like expectation maximization based clustering, which you could call a soft version of k-means, because k-means does something very similar. If you look at it, what you get around these centroids and the assignments of these points, you could basically also question, well, wouldn't it simply be possible that we try to fit a mixture of Gaussian models on top of the data that we have? And then the assignment is basically not something that needs to be hard anymore, but this leads you then something where you can say, it is possible for a point to fall halfway in one cluster and halfway into another cluster as well. This works with an EM-based algorithm. If you really want to do this, you could also kind of question, couldn't I just simply run k-means, and then for those points, based on the distances to the centroids of all the clusters, I can also kind of figure out that a point is halfway in between two clusters still. So wouldn't I be able to simply do the same thing with k-means anyway and get some kind of soft assignment by just inspecting the distances to the clusters? Then indeed, yeah, it would give you something very similar as what this thing does. So this is kind of the fitting that happens here. We're trying to fit Gaussians around our data, but very similar to k-means. Another benefit is, again, here you have a model for each cluster. So if you want to generate data points, new data points from that cluster, that would be nice with this because you get like a Gaussian for each cluster. But again, with k-means, why not just simply fit a Gaussian for each of the clusters with the mean and the centroids on the centroid and the variance derived using the min sum of squared errors? That would also work. So yeah, basically this does something very similar as what you can already get by standard k-means. Mean shift clustering, yeah, there is that idea of these kernels then a little bit. So what mean shift clustering does is it says, well, start with your data points that you have, and first put a small Gaussian centered around that data point on top of all of these data points. And basically then, what happens if you add up all of these Gaussians together, you get like a landscape that looks like this, right? Or viewing from the top, basically your fitted distribution, your KDE, your kernel density estimation surface will look something like this. And now what you can do, you have a very simple kind of mechanism now to do your clustering with. You just take these data points, you put them on top of this distribution, and you basically do some form of hill climbing. And for every iteration, you figure out what is the upwards gradient in this case, not as with stochastic gradient descent where we're trying to climb downwards, right? But basically you could invert the landscape and then it's basically also climbing downwards. But basically in every step, you just follow the gradient that moves a point closer to its local maximum. And in the end, what you will end up with is that, well, these points, they will all have moved to this location. And these points here at the bottom, they will all have moved to this location, and the points here at the top, they will have moved at this location. So when do you stop your iterating here? If you see that your points have kind of settled in their local optimum and they're not moving around anymore, right? Then you stop, and then basically you can just say, I have 3 clumps of points here now. They move to 3 positions, so probably those are the 3 clusters that I have here. Also pretty appealing, also pretty nice in practice, or a pretty nice method to know about as well. Yeah, the animation is on the web page, but it's basically the points moving to their local optima. Something, well, we spoke a little bit about the quality of a clustering result, and we saw SSE, and okay, if you have your centroids and you can calculate SSE, we did see that there are solutions with a better SSE than others, and probably that's something nice to keep under control or nice to keep minimal, so you can use the objective function of k-means to kind of get an idea of how good of a quality a clustering solution is. There are other measures as well, and they all try to kind of, again, figure out a trade-off between are you good at the same time at keeping high similarity within your clusters, and meanwhile keeping low similarity between your clusters. So the Davies-Boolean index, for instance, is a metric that tells something about the quality of a clustering solution. Now, that being said, yeah, if that's really what you want to optimize for, then sure, you can check that result. On the other hand, because this is unsupervised learning, and because something like a clustering solution can be very subjective, right? Also, the validation here, or using metrics like these, is at the end of the day will always be somewhat subjective as well. And there is no, of course, the problem is a little bit like, let's say that you want to implement a new algorithm to do clustering. What you will do, obviously, is you will hunt for data sets where someone has already came up with or established, like, this is the single true solution or the class memberships to the clusters for each of these instances. But of course, that's just a single solution. Who is to say that there isn't another clustering solution that is also good and also reveals something interesting about the data, but does not necessarily overlap 100% with this true assignment that someone has already made? A little bit harder in the case of unsupervised learning to do that. You don't really have true labels that it's important to kind of optimize for or important for you to learn, depending on what type of clustering technique that you're playing with, and whether you want something convex or whether you don't want something convex, or whether you want a lot of clusters or not a lot of clusters. There might be multiple viable solutions. So checking some basic metrics, of course, makes sense, but it's more important to consider, okay, but what is it that I'm planning to utilize this clustering for? Do I get the insights that I wanted to get by then looking at these clusters? Or if I may be using a clustering solution as some featureization technique in my pre-processing pipeline, where I utilize the distance of instances to centroids as features that I want to utilize, do these help, yes or no? And if they help, good, and then that help should be checked out by evaluating the results on a test set still at the end of the day. Right? But just looking at this, typically, or looking at metrics like these, are not all that revealing, to be honest. Also means, by the way, that looking at a test set, for something like k-means, that's pretty easy, right? If you would say, okay, I would like to utilize the distance between instances and the different centroids of the clusters that I have, and I would like to utilize those as features. And then tomorrow you get a new test instance. No problem there, right? You don't need to rerun your full k-means. In fact, we don't want to do that because this k-means clustering solution has become part of our overall learning pipeline. What we can just say is, okay, if you have a new point here, you can still calculate the distance to those centroids. Those haven't moved. It's something that you store as part of your model definition. Nothing needs to be done there. In the case of something like a mean shift clustering, yeah, that would also work. If you have a new point here, you would not recalculate this landscape. Right? You would not calculate the density estimation. That's something that you did based on your training data, but you could put a new point here and have it move to its correct spot as well. Right? Theoretically here, new points might move towards clusters that you didn't observe during training. So that's something that could happen, and maybe that you will need to account for. But that's something to keep in mind, at least in this case. Something like dbScan, there it's a bit harder. There you get a solution, but now if you have a new point, yeah, probably what you would do is you would look whether it falls in the neighborhood of points that you have already clustered, and then try to do your assignment that way, right? So that's also something that you could do, but it's probably going to be a little bit more nasty in the case of dbScan to do assignments there for new points. Not impossible, but just a little bit more difficult. So other applications, yeah, to recognize communities of people in social networks, that's something that we'll see later. But for spatial applications, in recommender systems, clustering is something that shows up all over the place. And also, as we saw in the case of image segmentation, or in the case of Lime, there we also saw k-means simply being applied to identify these groups of pixels in that case. What is also interesting to consider is if you have domain knowledge that you want to add in the clustering solution, how difficult versus how easy that would be. And domain knowledge typically is expressed in either I have two instances here, and even although my distance metric says that they are far away, I do want to have them ending up in the same cluster. That's something that you must keep them linked together. So this is typically expressed as a must link constraint. You might have instances where you might say, well, even although they are very similar according to this distance metric, I do not want to keep them in the same cluster, right? So in the case of k-means, this is relatively easy to add in because there you just change the assignment step to refuse to put some instances together in the same cluster or to have them be together in the same cluster. Depends also a little bit on whether your constraints are valid, right? Because you can specify a list of must link and cannot link constraints in such a way that no solution is possible anymore, obviously, right? If you cannot be with me in a cluster and you can also not be with a third person in a cluster, but we have to be together, I mean, you can end up in situations where there is no solution possible anymore. So you need to be a little bit careful, but some implementations also allow you to add in these types of constraints. Then distance metrics. Yeah, I already mentioned Jacquard and the cosine distance. If you would have a situation where your data contains both normal-looking continuous variables, but also like dummified categorical or simple categorical features as well, then you might have to find alternative representational schemes for these categorical values that work better on a numerical kind of distance comparison. You can look at things such as the Gower distance, which is a metric that tries to work for data which is both categorical and numerical. That mixes both types of features together, which is sometimes useful to know about as well. When you want to cluster small pieces of text together, you have a whole bunch of distance metrics that work on text, typically based on how many characters that you need to delete, insert, or substitute to kind of see how many steps does it take to go from one text to another text. But that then starts to fail when you would be working with larger documents, obviously. So with larger documents, there you would today utilize something like sentence embedding embedders. You would buy an API key at OpenAI to basically get a numerical representation for a piece of text that you have. And then you just utilize cosine distance on these numerical representations to cluster them together instead. Same for images. You would utilize something like perceptual loss, for instance, is something that can tell you the distance between two images. And typically, they use exactly what we have seen previously, is that you ask some pre-trained deep neural network to basically give some measure of distance in terms of how similar are these two images to one another. So perceptual loss is a library, for instance, that you can download that does exactly that. Direct distance comparisons on input images directly, even though in some cases done, where you just calculate the difference between each pixel and you also kind of square it and you add it all together, can work, but very often you do not end up with images going into the same cluster in the same way as if it's objects that you're interested in, for instance, and you would like to have all the dogs in the same cluster and all the cats in the same cluster. Doing that directly on the color space of images is not going to work. It's just going to put all light colored dogs and cats in one cluster and dark colored dogs and cats in another cluster. So that's why you typically need to look at another distance metric or similarity metric to do those sorts of clusterings. But those exist, so you can also find distance metrics that work on images as well, more on a perceptual level rather than a color space level. As a very small in between, but we're not going to talk too much about this, but this is just like you could call this an honorable mention, but also an interesting kind of in-between case, because this kind of brings us from the space of clustering more towards dimensionality reduction, and also is a good highlight of sometimes both of them can mix with one another or can have similar concerns. I just told you, well, for the case where you have a lot of features and you would like to visualize your clusters on some kind of two-dimensional overview, typically what you could do is, well, either you run something like a PCA first and then you cluster on the components, or you first cluster and then utilize PCA to show it in 2 dimensions, right? So another technique that does something or has like a similar idea It's a pretty old technique by now, but it's called a self-organizing map. And a self-organizing map also says, well, you can actually express it as a type of a neural network as well, but typically that makes the explanation a bit harder. So a more easy explanation is we're going to first create a two-dimensional grid, and that is typically a hexagonal grid like you see here, but it could be squares as well, or it could be triangles. Everything that covers perfectly a partition of 2D space is possible to utilize. Typically hexagons. You decide on the size of the grid, so how large all of the hexagons should be, the resolution of the grid as well. And you also need to specify a neighborhood function. But typically, when you have a nicely covered tiling system like this, of course, the neighborhood of each hexagon are the ones that touch its edges, right? So that's the neighborhood. And then basically what this thing does is it starts by putting in a randomly generated vector of the same size as your dimensions are of the features that you're utilizing. And then it basically iteratively goes through also some sort of assignment where it says, okay, in which hexagon does every instance fit best in? So again, based on distance between the vector that represents or that's included in the hexagon versus the feature vector that you have, based on the most similar pairing there, we can assign every instance to a hexagon. And then also the representations get updated because after doing this assignment, just as we moved our centroids around in the case of k-means, also here, because we have assigned instances, we can probably update our vector to be some kind of average, let's say, of the instances that we have assigned. The thing that is a little bit more special here is that every time that we move this vector around, it also updates a little bit the vectors of its neighbors as well. And at the end, you get kind of a self-organizing layout where your data has laid itself out to belong to one of these hexagons that you see. And then the idea is that you can start playing with this and you say, well, okay, based on the age feature, for instance, what do the instances that have located themselves in here look like? High values are in red and low values are in blue, right? And then based on another feature, like no idea what this is, let's say income, high income over here and low income over there. And then by basically looking at cross intersections of these colored spaces for your features, you can again try to identify regions where, hey, here are the high income people with a low age, for instance, and here are the low income people with a low age and so on. And then to kind of make this visualization a bit easier, what you kind of see here, what you get is, in a sense, we have given now, or we are able to give, because every instance is now positioned in one of these grid cells, what we have basically done here, or what this is kind of doing, is it's not so much clustering, because this is no clustering solution, it's a dimensionality reduction. It basically has tried to find a position for each instance in 2D space. So also this is a dimensionality reduction technique, where we are constrained to 2 dimensions, although you could think of a grid that works in 3 dimensions, if you can find some neighborhood function or you pack circles together. And of course, it's a bit more constrained because you have this underlying grid there. What you could then do is you could then run k-means or something over these values that you get out of this 2-dimensional positioning, and then you do have clusters on top of this thing. But in essence, it's a dimensionality reduction technique. But what it does reveal is that it's quite common that dimensionality reduction is combined with clustering, because with dimensionality reduction you get the position in 2D space, but then you still would like to see the groups, so you run a clustering on top of it. Now, not a lot of detail, because self-organizing maps, they're barely used anymore. PCA is a bit more common, right? But this does lead us to some other dimensionality reduction techniques that are very common nowadays and that you do need to know about. First, then we will go for a break. But first, if you don't know how PCA works, read up on it. It's calculated by making use of the eigenvector decomposition of the covariance matrix of the data. Basically, you try to keep as much of the variance in your reduced dimensional space than in the original dimensional space. I always like to kind of look at it like if you start with your 3 dimensions in your original feature space, what you're basically trying to do is, if you're mapping to 2 dimensions, is that you're trying to position yourself with a camera and trying to find the right angle to the data that keeps as much as the variance intact, right? Of course, that becomes harder if you would be mapping from a 10-dimensional to a 3-dimensional space, but it's kind of the same concept there. Now, it's a linear approach at the end of the day. So it's a linear transformation that you apply to map your data. It can be applied on test cases, so that is nice, right? It's a representation of the data with a particular focus on keeping that variance around. Yeah, drawback, these components might be a bit difficult to interpret, but that's always the case for a dimensionality reduction technique. So has a lot of pros, is fast, works well, but the next dimensionality reduction techniques that we will look at, they will basically change this approach and they will say, well, what if instead of asking how can we best retain distances between data points that were far away from each other in the original feature space, how can we best retain that variance in the reduced feature space? But is that the only way how we can look at this problem? We could also say, well, what if we do not care about points once they're sufficiently far away from each other, but we care about points that are sufficiently close to one another, that they also stay close to one another in the reduced dimensional space. And then once they're too far away anyway, that's not really our focus, right? We care about things that were close to one another and keeping those close to one another. What type of reduced feature spaces or reduced dimensional spaces do you then end up with? That's something that we'll see after the break when we talk about t-SNE and UMAP. So first, let us do a 15-minute break. All right. We continue with t-SNE. t-SNE is by now already a bit of an older dimensionality reduction technique, all the way back to 2008, by, again, Geoffrey Hinton on the paper, together with Van der Maten. It's a dimensionality reduction technique which is based on manifold learning, and it's not the first manifold dimensionality reduction technique that has been proposed. You have IsoMAP, locally linear embeddings. In fact, also autoencoders can be regarded as a technique that tries to learn a manifold over the data. What is a manifold? Mathematical concept that we do not need to talk too much about, but basically makes an assumption, or a manifold is a topological space that locally resembles Euclidean space. So in other words, a normal behaving surface, there basically, whenever you take 2 points in here, wherever they are, if you would take the space between them, that will be Euclidean space, right? So there is nothing weird going on there. What basically a manifold tries to do is say, okay, but what if you have a higher dimensional kind of data structure? And let's say that we would work in 3 dimensions, because going higher than that, I have difficulties to draw that. And you have data points in this 3-dimensional or higher dimensional structure. How can I basically figure out a way to construct or to learn the manifold that fits these data points well? And so basically what I'm trying to do is I'm trying to curve this surface and to position it in such a way that, and now I will kind of give an example, where for instance, if in 3D space my points would be organized as kind of like a U shape in 3D space and going into the background there, then probably a surface that is curved along this way would be a good description of that manifold. And then basically the idea is, okay, now if I utilized a 2-dimensional manifold to fit these points with, and my original 3D data points, they were located here, so they follow this U curved shaped structure. What do I then do if I need to represent this original higher dimensional thing in 2-dimensional space? Well, basically you have it then. You take this 2-dimensional surface that you fitted on top of your, or on your original high dimensional data, you lay that manifold flat on the ground again, and you basically then have your 2-dimensional representation that will look something like this, because this is what happens if I curve this open and I make this look like this. Locally, if I stay close around, or if I take points that are close to one another on this manifold, and if I take the Euclidean distance between these points, then probably this will match pretty well with the Euclidean distance that these points had in the original feature space. So local distances are retained both on the manifold and in the original feature space. What was close to begin with will stay close when I view this manifold that I fitted on top of it. But if I take points that are far away from each other on this manifold, there it might be that the Euclidean distance that I have in this 2-dimensional space does not correspond with the distance that I have in my original feature space. So basically, when points are close to one another, I know that they were close to one another in my original feature space. But then as they get further away from each other, that doesn't necessarily mean that they were far away from each other in my original feature space. So here, this is trying to do kind of the opposite as what we were trying to do with PCA. Now, how does it do so? That is why manifolds are an interesting mathematical construct, but in fact, to know how t-SNE work, you don't need to know a lot about them. Basically, what it ends up doing is constructing something that looks like a manifold, but the actual optimization procedure is in fact quite simple. Basically, it works in two steps. We first extract a probability distribution, measuring again similarity for pairs in our high dimensional space, in our original feature space. Then we do something similar. We will also need something that can measure this probability distribution over data points in a low dimensional representation. And basically what we can then do, if we then have our solution in our original feature space, we have a pairwise kind of distance matrix between instances in my original feature space. And then I would ask you, okay, given a map, given a surface, a two-dimensional surface, find me, that's basically the task that you try to do, find me a position for all of the instances that we have in this reduced feature space. And then based on the actual solution that you're proposing, I can calculate the pairwise distance matrix between all instances that I have in your solution. That's going to change, because you'll probably use this to move the points around and to make your solution better and better and better. If you're already thinking, using stochastic gradient descent, perhaps, then you're already coming quite close, right? And basically, I will check whether the probability distribution that you have in your reduced feature space, that this matches with the probability distribution that I had in the original feature space. And then every time people are saying, well, you're matching or you're measuring the degree of similarity between two distributions, well, we already have done that before. We already used the KL divergence when we spoke about variational autoencoders, for instance, to do the exact same thing there. But also here we're using typically KL to measure how these two distributions are similar to one another. You could also use JS, you could also use the Earth's mover distance, although that will probably be way slower in this case, but the default technique uses KL divergence, relative entropy. So step one, we are going to measure similarities between data points in our original high dimensional space. So the similarity of a point xj to xi is the conditional probability, pj given I, that xi would pick xj as its neighbor if neighbors were picked in proportion to their probability density, assuming a Gaussian kernel which we have centered around this point xi. So basically, the way how we calculate this metric pj given I is we are looking at I, we plot like a Gaussian around it, and based on that distribution, we basically see, well, how close is j to I, basically. So the further away, the more that this will go to 0, right? And of course, you'll have to play a bit with your bandwidth setting and stuff, what this Gaussian actually looks like, that we come to that in a second. Okay, good. And we don't need to do that for this j and y only. We do that for all of our data point pairs. And then basically, because we need to do that in the two directions. So now we have it. What is the probability that I would pick j as its neighbor? We also need to calculate it the other way around. So we also need to calculate what is the probability that j would pick I as its neighbor, right? So that's why we have in that formula on the right-hand side, we calculated this huge-looking thing, but that's basically this Gaussian that we plot around this thing for both j given I, for I given j, and then we normalize given that we have 2 dimensions, for instance, which is in this case n is equal to 2, because in our toy data set we just have an x1 and an x2. Normally, your higher dimensional space is not 2-dimensional, but again, to kind of show the visuals here on the slide, we start from something that's already 2-dimensional. So that toy example does not make a lot of sense. And we also assume, but that's because we need that in our distance comparison, that the distance to a point to itself is 0, basically. Okay, good. What does this mean? Well, basically, again, here the highlighted idea around it. So we plot like a Gaussian kernel, a Gaussian distribution centered around xi. And what do we see? Well, what is the probability that I would pick j as its neighbor? Well, 0.78 normalized by this denominator here that we utilize to normalize all of these values Yeah, and k, of course, what is the value for this? That this one would be chosen as the neighbor for I? Well, lower, of course, because k is further away than j is, right? So basically, we got like some sort of distance values coming from Gaussian distributions that we center around each data point that we use as kind of distance values here. But this is a full probability distribution because, of course, we are normalizing by this z factor. So all the similarity measures are normalized against all points except the point itself. So basically, that's also something that you can just calculate accordingly. And then basically, you have a whole matrix of numbers like this. Okay, but we also need to have the full joint probabilities, because now I just did that for the formula j given I and k given I, but we also need to swap that around. We need I given j as well to actually get our correct probability distribution, so we also calculate that. And we divide by 2 times 2 because we have 2 dimensions, 2 by 2, and these are then our final joint probabilities that we can put in our matrix. So all of these will be, of course, pretty close to 0 because we have a lot of instances, right? And our matrix is already quite large. But basically here we have similarity values between pairs of points. That's basically what we attempt to calculate here with this joint probability distribution. So here we can indeed see that, yeah, I and j, they are more similar than I and k are to one another, because also the final value that we end up at obviously is larger here. So they are closer to one another. So the closer that these instances are, the higher that this probability value that they will get will be. Except for the instance itself, where we override it with 0 because we need that to make the rest of the system work. Okay, so this is based on Euclidean distance at the end of the day, because what you can kind of see about these numbers will end up behaving like is you can play with the bandwidth again of this Gaussian that you center around each of these points. And so if you have a point and you fit your Gaussian to look like this, or you fit it more to look like this, in this narrow case, only points that are very close to the original point will get a high similarity measure. But from the moment you step away a little bit further, your value will drop to basically 0 almost, right? So basically with this bandwidth setting, with this narrowness setting, you have control in terms of what do we consider the kind of effective neighborhood to be around points. How far should we look around each point to kind of establish who is nearby and who is already too far away, right? Similar to k-nearest neighbors a little bit, similar to what we did with dbScan just now, where we also defined like a neighborhood size. So also here we're kind of defining like what's the neighborhood that you want to look in. Interestingly enough, and that's also the reason why you need this j to I and I given j, and that this works in 2 directions, is because this bandwidth parameter, this sigma that appears in the formula, the way how this is calculated, it shows up in here as the bandwidth, but this subscript I reveals that this bandwidth is data point dependent. You get a different bandwidth per data point. And the reason why this is done is because if you look at data sets, of course, their density that they have, especially in original feature space, the density that they have will vary across space. You might have regions where points are very close to one another and where it makes more sense to use a little bit of a more narrower Gaussian around that point. But then you might have regions in your data set where points are more spread out. And then if you would take too narrow of a bandwidth, then you would basically not be looking at any neighbors anymore. So there you would have to go wider. So t-SNE makes a choice to fit this Gaussian or to have this Gaussian around each point with a instance-dependent bandwidth size. Now, it wouldn't be fun for a user if they would have to pick this sigma I for every value of I. So if you would have 10,000 data points, that the technique would ask you, okay, and now please set a bandwidth for each of them separately. That would obviously not work, right? So what it tries instead, or what it offers instead, is a single perplexity parameter. And that's something that you can set. And basically on this perplexity parameter, they will, or the technique or the algorithm will itself dynamically figure out what the correct bandwidth should be for each data point by referring to this perplexity parameter, which is basically an indication of how well should a distribution predict a sample. And then basically it will be able to see, okay, for regions where we are very dense, that bandwidth can be kept quite narrow, and for regions where we're very sparse, that bandwidth can be increased. So it's still picking a separate bandwidth for each data point, but it's basing it on a single parameter that you set, and that single parameter will basically boil down to you saying, well, how good do these distributions need to fit their surrounding samples or the other samples, basically? And do I only want to look very close, or do I want these distributions to also cover a wider range? but then it still can be adapted based on the density of the data. So smaller values will be used in denser parts of the data space. A bit similar to adaptive bandwidth methods that you might have encountered in geographically weighted regression, for instance, where something very similar is done. Because there, if you work with spatial data, you have similar issues. If you make point measurements, you will have regions where you have a lot of measurements very close to one another, but then maybe in more rural regions or something like that, your measurements might be more spread out. So also there, if you want to do interpolation, and you need to predict on a certain point in a map what's the value if I would measure here. Well, the points that you would include in your prediction to do that, if you're in a dense region, you will probably not look very far. You will only look at kind of the points that are very close by. If you're in a region which is more rural and less dense, probably there you would have to give a higher importance to points that are further away because you simply are in a less denser area of the space. So this is a key hyperparameter, or this is the key hyperparameter of t-SNE. Fine, we then have, basically what we get is a big matrix for every pair of instances that we have that tell us how similar that these points are to one another. Step 2 is that we do the exact same thing, but we do it for the position of our points in our low dimensional space. So also there, we look at how similar are these, but there we use a simpler distribution to do that because it has fatter tails than the Gaussian distribution. We use the student t distribution there. Also there, same assumption that qii is 0, right? So points are not similar to each other at all, to themselves at all, to make the divergence matching work. And there also, crucially, there is no perplexity parameter. So when we plot these student t distributions, which look very similar than these Gaussians, right? But they are just a little bit fatter around points. Here we do use the same bandwidth for each of the data points. The reason being is that when we are putting our embedded or dimensionality reduced points in this space, yeah, we can work with a constant bandwidth. If that doesn't work, then move the points to make it work better. In other words, what you will end up getting by doing this is that in your dimensionality reduced space, you will have a similar amount of density no matter where you are in that reduced space. So there you will not have varying amounts of density anymore, right? And that's probably exactly what we want, is that there we have like a nice, well-behaving space in terms of density. So we have these two matrices, one for P, one for Q, one for the higher dimensional space, one for the lower dimensional space, and we calculate the Kullback-Leibler divergence to kind of see, well, how similar are these probability distributions to one another? And that's the one that we want to minimize. That's effectively our loss function. How can we minimize that? Well, use any sort of iterative approach, but we know one that works well, which is standard gradient descent. So basically all the weights, quote unquote, in this model, or the parameters that we are now optimizing for, are the x and y positions of my reduced points. Those are the ones that I'm shuffling around in every epoch, or in every step, I should say rather, until I find good converged values. And the loss function that I'm minimizing is this KL thing, using P and Q matrices that are calculated on the original and on the reduced. And on the original, that P matrix, I only need to calculate once, obviously, right? Because there the points do not move. If I have it, it stays the same. For the Q one, I do need to recalculate it, but that is not such a big deal of work because I'm not even using a perplexity parameter there. I'm using a simple student t distribution as well. It's probably an operation that can be implemented also straight on the GPU to calculate this thing, right? So then we shuffle the points around. What is found is that t-SNE is one of the techniques that can work extremely well if you deal with very high dimensional data. So this is one of the embedding techniques or dimensionality reduction techniques where you can work straight on the raw data that you have of images, raw pixel data, and directly try to find locations on a two-dimensional kind of embedding map. And very often, the way how it will lay out the images will be based on brightness for one dimension, but it's not really dimensions here because we have learned a manifold, right? So that's something that we do need to be a bit careful about. And color maybe for another quote-unquote dimension. Now this dimension thing, so this is something, it's a bit dangerous to mention that. So what you get here is, if you look at this t-SNE map, which typically will be something that reduces towards 2 or 3 kind of dimensions. But if you look at the axes, this is not like a fully dimensional construct, right? The 2 dimensions here are basically more represent of Well, you have an available 2D space and you're trying to map, to embed good locations for these original instances that you had. Right? It's not like with PCA that one dimension is like a linear combination of these things and the other dimension is a linear combination of those things. Right? Here it's more like the technique has learned to place all of the original instances on this map. Right? Where if you would run it again, that basically it could come up with a rotated solution or something like that, right? But that's basically what it tries to do. And placing it in such a way that, and again, this is why you need to be careful with these distances. If you look at images that are close to one another here, that these are still similar. But where you can't really say, look at this image and look at the image all the way on the other side, and they are so far apart across dimension 1 on the x-axis, for t-SNE that doesn't make sense to get something like that out of this solution. Right? It's placing images on this map. Placing them in such a way that, yeah, probably for many downstream tasks, it will still be linearly separable in some way, or well separable in some way. So for that, it still makes a lot of sense. But be careful in terms of then calculating distances now as well on this reduced feature space. That's something that you should be a little bit wary of, not to do that. That's been done with images or with word vectors, right? Here are the words dimensionality reduced in a 3-dimensional space, and so also you see clumps of similar words ending up together around each other. This is based on news articles from both left-wing and right-wing outlets, and this was during the first or the first time that Trump came into power, and basically scraped a bunch of news articles from the left-wing outlets, same for the right-wing outlets, use word2vec to get word vector representations for them, then embed them using t-SNE in a 3-dimensional space, and kind of then analyzing if you see interesting differences between the two political orientations there. What you also see is that t-SNE itself, you just get a position for each of your instances. So t-SNE itself is a dimensionality reduction technique, not a clustering technique. Of course, what is very easy to do is if you end up with a map such as this one, is to then say, well, I can still now run k-means or dbScan on this 2-dimensional structure and find clusters that way. And typically that's something that actually works quite well, but you should be a little bit careful by doing this. And the careful part is, well, the reason why this works quite well is because most clustering techniques, they also will look at, well, local distances to perform their clustering mainly, right? So they're also not really trying to keep variance intact, so which is why they work well. Like something like a dbScan, we saw that exactly there. It also just considers like the very close neighborhood around each point to form these clusters. With k-means, yeah, there it depends probably a little bit on how many clusters that you are creating. So also there, the answer again should be create sufficient of them to do that. But hence why dbScan works a bit better in this case than k-means works, because you might end up with comparisons over longer distances, which is less meaningful in an embedded space like the one produced by t-SNE. There is no hard reason why this is the case, but most t-SNE implementations will force you to pick either 2 dimensions or 3 for your reduced dimensional space. The main reason is that if you'd like to go higher, there is nothing in this setup where you wouldn't be able to place points in a 4-dimensional space, for instance, except that maybe you can't get as nice looking pictures anymore in that case, but you could. You could still compare the KL divergence and measure that. The reason is that then it becomes too computationally expensive. And so typically most implementations stop at the 3rd dimension. What is also annoying is that, and this is the biggest drawback actually of using this as a dimensionality reduction technique, at least in the way how we have just described it, is that it does not learn a parametric mapping. Meaning that the next time that you have a new instance and you would like to ask your trained t-SNE model, where should I place this instance in this 2-dimensional map, then it cannot do that for you. It doesn't learn a function that maps data from input space to your mapped space. No, we are just, these points are parameters. These are the ones that we are optimizing for, right? Effectively, the data points are our model. We don't learn how we can place a new point in this map. So it's not possible to embed unseen points in an existing map. So that means that this is less suitable as a technique that you would use in a predictive setup, because there you will have new instances that you need to place in that map. However, of course, if you think a little bit about it, right, you could also say, well, isn't it possible to set up a model that rather than trying to place or position all of these instances directly in this two-dimensional space, where they maybe learn how to map from the high-dimensional space to 2 dimensions in such a way that we still then minimize the same loss function that we had previously. And indeed, that's called then parametric t-SNE. Those versions do exist. But do make sure if you be planning to utilize t-SNE in a predictive setup, that then probably it is important that you then look that you have a parametric version instead of the default non-parametric one, if you need to fit new instances. You could also provide your own similarity matrix, should you want to, instead of the way how it's done here, and use KL minimization instead of the built-in conditional probabilities that it uses. That's a choice that it makes, but you could also utilize your own distance matrix if you'd like to deviate from that. In that case, this might even help you or avoid you that you have to tune that perplexity metric yourself. In the end, what you do still have to tune then is which distance metric you utilize to construct that matrix with. Uses a gradient descent-based approach, so the same thing, learning rates and so on, and the initialization of these mapped points, because these are effectively or parameters. This also plays a role in this context as well. So all of these kind of hurdles, they do also show up in this algorithm of t-SNE. So what is typically done is that for the initial positioning of the points, you just start with what PCA gave you as the solution. And you run PCA, you get the 2 principal components, and you use that as positions for your points to start running t-SNE with. That seems to be like a good starting point. What you will have to tune is perplexity, and this is basically what is the size of your effective neighborhood that you consider. It's a bit similar as what the K in that KNN is. Depends still on the density of the data, even although it assigns every data point a separate bandwidth value, it is still a bit sensitive to the density of your, or the overall density of your data. Denser data typically needs a larger perplexity to work well. So the impact of perplexity is the neighborhood that you effectively consider around points of interest, or around points that you have. This is the largest drawback, you could say, of t-SNE, is that different perplexity values can lead to completely different looking results. And this is sometimes why you should be careful with applying clustering techniques on these embedding maps, or you should be applied on interpreting distances between clusters. In the case of t-SNE, the size of clusters actually has no meaning. The distance between clusters also has no meaning. The only thing that really has meaning is that you can say if things are close to one another in your reduced feature space, that they were close to one another in the original. But this solution says so does this solution, so does this solution, right? This is a solution that breaks because you've made the perplexity parameter way too large, and basically now you're considering that everything is close to each other, right? Yeah, then of course everything ends up as one giant lump in your embedded space as well. So that's the most important parameter to tune. How do people tune this? Well, typically just visually, right? By inspecting the results and then probably ending up with something that does look like clusters, even although you know that these are not really clusters, but this is something that then a downstream model can nicely separate the data with and things like that. So, but it is a parameter that you have to tune. The original release was MATLAB based, but of course you have packages in R and Python available. It's implemented in scikit-learn out of the box. You have many other implementations. There's also an example to a parametric version, but you can find other implementations of that as well. Now, the fact that you need to tune this perplexity parameter with t-SNE, and the fact that it can be a bit sensitive to that, caused another algorithm to be developed a little bit later, 10 years later in 2018, by a different bunch of people. Very similar ideas as t-SNE has. Stands for Uniform Manifold Approximation and Projection 4-Dimension Reduction, a whole mouthful. It's also comparable in terms of what it aims to do to other dimensionality reduction techniques. Like t-SNE, it builds a nonlinear representation, also based on manifold learning. It's newer, but for some reason the bioinformatics people really love it. They very often show like cell atlas maps where they do like a dimensionality reduction using UMAP. Because your regional feature space is basically the readings for a whole bunch of gene expressions that you have, which is a vector with an enormous length. So then they reduce that and they plot every cell that they scanned in this 2-dimensional map, and then they try to say, well, here is a group of these cells, so must mean that these other cells are also of that type, and things like that. So they tend to use that quite often. It allows you to perform mappings with a dimensionality higher than 3, and performs better, but typically people also stick to two-dimensional or three-dimensional mappings when utilizing this. Something cool is that here they also allow you, if you have labels, to utilize these labels during the construction of the map itself. So to already position your instances in such a way that they lead to better separability based on the classes that you have. It's parametric by default, which is also a plus, so you can also map new unseen points using this technique as well. Works a bit better than t-SNE does in terms of speed, in terms of performance. So it has a whole bunch of nice properties, which is the main reason why this is now the one that is preferred above t-SNE and is used as a drop-in replacement and also works well with high-dimensional data. So this is an example where there are small images of pieces of clothing that have been used as the original instances, and they have 10 labels. Just using the image data directly, using UMAP in the supervised way, you already see that the way of it, how it has embedded the data and structured the data match extremely well with what these 10 labels are. You can then basically take like a very simple, even decision tree model that you would just run on top of the X and Y coordinates here, and you would probably get like a good classification model out of this. It doesn't always work so well, but it is a very nice dimensionality reduction technique. Just to give an example, like this is one of the more recent publications from Stanford, where they are talking about a tool to identify and annotate cell types across single cell experiments. It has the ability to discover and suggest human interpretable names to novel cell types that have never been seen in previously annotated experiments. What's the map that they show in the middle, and what is the approach that they use to base that on, to find these landmarks and to identify these cells? Well, this map is a UMAP constructed map, basically. So a lot of this kind of work is based on dimensionality reduction. When we spoke about, and now we come back there, and we spoke about making CNN models more interpretable, I said, well, you could run an embedding directly on the images and position them. You could also take the activation vectors before the last layer, which is typically also high dimensional. You could also embed those activation vectors, and you have an activation vector per instance. So in the map that you show, you could still decide to show like an image like it's done here, right? And I said, well, what would be the difference? Well, probably in the embedding that you get, given that you run UMAP in an unsupervised way. For the images, probably there, the structure that has a lot to do with color of the image and brightness of the image and so on will be retained, because that's what you see, that's the pattern that you have. If you would map the activation vectors that come out of a model that was trained with a classification downstream task, there you would probably see a result that looks more similar like this thing already is, because there you know that, okay, the layer that comes after this one will probably have the job of separating these classes. So we don't really want to make groups based on color of the image, we want to make groups based on what the content of the image was. Here with supervised UMAP, you don't even need to train a model, you can already get like a good starting embedding if you have classes by doing this. Python has an implementation that works or is scikit-learn compatible, so that's the preferred one, or also has not one, but for some reason multiple packages that implement UMAP. But still one of the most well-known dimensionality reduction techniques, and something that you will definitely at some point use to visualize, to embed things, to lay out images, or to inspect results of another model. Then we can talk a bit about anomaly detection. So outlier detection or novelty detection. Here our job is we would like to find, well, not the things that are most frequent in a data set, that can be interesting, but things that are like anomalous. And anomaly detection, it is a bit related to outlier detection, obviously, or noise detection or novelty detection, but the tasks are a little bit more nuanced in a lot of cases. Like typically you will see anomaly detection in cases such as, let's say, fraud detection, where you're looking for fraudulent claims or fraudulent transactions. These are things that really happen, so in that sense it's not like outliers that you would remove from your data set. Here the whole task is I would like to hunt for these cases that are a bit weird, a bit strange, a bit anomalous, right? Without necessarily removing them from my data set. So the way how we saw outlier removal in the pre-processing session was there we know, okay, this is probably noise, we want to remove this and so on. Here we are specifically hunting for these type of anomalies. So defects, medical errors, fraud, that sort of stuff. Typically also, if you think about use cases such as fraud, probably these fraudsters are going to do like an actively good job in trying to conceal their behavior. So probably you also know that the set of techniques that you will utilize is, if the goal is really to do anomaly detection, will also involve that you will have to step a little bit away from these typically univariate approaches as you would use them during pre-processing, because there you want to keep it simple. You calculate something like a z-score and you remove outliers or you clamp them based on that. But here probably you would like to utilize something which can extract like multivariate kind of relationships that make something kind of anomalous, right? So statistical approaches, yeah, they can work, but I mean, if you already look at this toy example with 2 dimensions, it's not even identifying all the outliers here correctly. So nah, that will probably stop to work in many cases. What are other ideas that we could do? Well, we already saw some of them. Like one thing that you could do is to apply clustering techniques and checking which instances fall outside of the clusters based on distance, based on clusters that have a few instances, for instance, based on the dendrogram that we saw previously, based on the noisy instances that you get from a dbScan clustering result, right? These are typically also your anomalous cases. Can be combined as well with dimensionality reduction techniques as we saw just now. You could first run UMAP and then you run your dbScan on top of that and then start to investigate the noisy points. Like, are they indeed anomalous cases? Why are they anomalous? And so on. So that might be one way. This is an example of someone who did exactly this, back then still using t-SNE to kind of hunt for anomalous instances in, I think it was railroad data or train data, something like that. Already a bit of an older article. But this is something that you can do. Another technique that is sometimes applied here, but less common also nowadays, is to use one-class SVMs. One-class SVMs are basically support vector machines that assume only the presence of a single class, right? And try to fit a model that fits the majority of your cases that you have as well as possible. And then everything that falls outside of the model can then again be considered to be outliers or to be anomalous. A bit linked to positive labeled learning. In the case of one-class SVM, it basically you don't need a label because it will just try to fit a model well around the data that you have. But why this is linked is that the reason or the case where you always or where you see a lot of anomaly detection techniques showing up as well, or exactly, and fraud is again a very good example of this. In the case of fraud, what you typically have is not only do you have a high degree of class imbalance, so you have way less positive cases, hopefully, than negative cases. It's also a bit biased in the sense that your positive cases, there are probably cases that you have identified in the past that you did some analysis for or some investigation for, and you have confirmed those cases to indeed be fraudulent, to indeed be positive. So of those, you're sure. But the negative cases, or the cases that you call negatives, probably there, how many of those have you actually investigated and confirmed that they were negative? Probably not a lot of them. Do you even keep track of that? So probably you also still have some positive cases that are hiding in the negative side. And that's exactly then what happens if you train a normal supervised model. What will end up happening then is, even if that model does a good job, that people will tell you, yeah, but your model is just identifying the same types of positive cases or fraudulent cases that we would already have spotted nonetheless, right? It's basically just doing what we already could do. So why can't your model find some new types of fraud? If you don't have the labels, good luck with a supervised model to hunt that out. So typically there you would first use an anomaly detection technique to already make a short list of cases that look strange and try to utilize this to have more of the cases that you can label as being a positive going forward, right? That model is, or an anomaly detection technique is typically unsupervised, but what you do find is that very often it can help to detect cases which are not only strange, but indeed also fraudulent. We already saw another technique that can help us to do anomaly detection, in fact. Might be mentioned later, I forgot if I put it in here, but just to repeat it now, our outlier, or autoencoder was also something that we could use to perform anomaly detection by comparing the reconstruction loss of our instances, and the harder it is to reconstruct an instance, the more of an anomaly it probably is. So autoencoders and even variational autoencoders are also quite commonly utilized for anomaly detection. And then there is another technique, which is quite performant and quite interesting, and that technique is called isolation forests. And this is a technique which is kind of very similar to how a random forest works. And remember, with a random forest, we had our labels and we just build our decision trees, and in every split of every decision tree, we randomly pick a subset of features to consider to calculate the information gain on. An isolation forest says, well, you don't have labels, so it's unsupervised, so that's already a first difference. But also you could call it an extremely randomized version of a random forest. Because this one says, okay, every time you're building one of your decision trees and you need to pick a split, you need to pick a rule to perform a split with, just close your eyes and randomly pick a feature. Without checking anything, without information gain, hocus pocus, just randomly pick a feature. And for the splitting point, temperature lower than equal what? Well, also for that, for the split point, also just pick a random value that you could pick. From the list of values that you have observed in your training data, or the list of values that we would have considered to calculate the information gain for in the case of a random forest, just pick a random value. And then the idea is that we will, and that's also, well, we did that as well with a random forest, but there we didn't have to, but here we will. Here also, we will continue building every decision tree up until every instance is fully isolated, is in its own little tiny box, orthogonally speaking. So it's almost like we are on the one hand extremely randomizing and on the other hand also overfitting in a way, right? But again, we have this variance reduction because we don't build just a single decision tree, we still build a whole bunch of them. Now thinking about it, if I have a data set where I have a lot of common points over here and there are like some random outliers over here. And I close my eyes and I pick a random feature to split on. I only have two, right? X and Y. So, whoop, first split, second split, third split, fourth split, fifth split, sixth split, seventh split, and so on, 8 splits. If I then inspect my decision tree, if I do this all the way until everybody's in their own little box, and I would start from the root node and follow the pathway to go to a certain instance that is now in one of these leaf nodes. If you're anomalous, will it take more steps to become isolated or will it take less steps to become isolated? Less. Yeah. It's a sad story of life that the more of an anomaly you are, the easier it is to get isolated, right? But also here, that's kind of what happens. So what it then does is it calculates an anomaly score by just looking at the number of steps that it took to isolate you, and the more steps that it took, the less of an anomaly that you are. And it averages them over a bunch of decision trees. That's the basic way how this technique works. And this, if you compare then so the decision or the heat map here shows the anomaly scores for all of the instances, this tends to work extremely well, also with trying to spot non-linearities in a multivariate way with multiple features and so on. So this is a technique that in a lot of use cases, like fraud, where we utilize it, for instance, where it can work extremely well with a very low amount, because that's what it still gets from random forests as well, with a very low amount of pre-processing that is necessary as well. So very interesting, a very well-performing technique. In many cases, even outperforming, like if you work with tabular data, outperforming like what an autoencoder would be able to do for you. Another interesting technique is that of, that's also good anomaly detection technique, is that of local outlier factors. It's kind of based on, again, the neighborhood idea that we already saw in KNN and in Perplexity, and that shows up all over the place, is, okay, what we can do is we can measure the local deviation of density of a given sample. So I'm basically looking at a sample, and I'm taking a look at who are your 5 nearest neighbors, and how close are you? Is there a lot of variety in there, or are they all far away from you, or are they all close to you? So we keep track of the distance between you and your 5 closest neighbors. And then I go ask the 5 neighbors, hey, between you and your 5 closest neighbors, what's the distance there? And then the idea is that for anomalies, that variation of density between a sample and what the density of distances are between the neighbors, if you would ask them, that this is a measure of, again, that can measure how isolated an object is with respect to your surrounding neighborhood. So again, this is based on comparing densities and to see, well, if you're all close together, that's all nice. But if then the neighbors of you, they are all far away apart from each other, it must mean that you, even although you are close together with some of your neighbors, their neighbors are not anymore. So it means that you already form some kind of isolated kind of island. So here, the larger the ring is, the visualization is a bit messy, but basically what is being drawn here is the size of the circle around each point here indicates the anomaly score that's been assigned. And you can see that for this point, even although it has like neighbors that are all kind of similarly far away. But if we ask these neighbors, for instance, how close they are to their neighbors, then suddenly the density shifts rapidly, right? Yes, okay, you're far away to all of your neighbors, but then if we ask some of your neighbors, suddenly they are close to a lot of other points. So you're kind of on your own still far away from the rest of the group, or far away from the rest of the closest instances. So that's another technique that tends to work quite well. Drawback here is that you do need to tune like a k value again. With isolation force, there is basically nothing to tune. So that's why maybe still a little bit preferred, but local outlier factor can also work quite well. Yeah, and here, so recall that the reconstruction error of a variational autoencoder can also be utilized as a way to get anomaly scores. You can also try to get a little bit clever or tricky. This is a very old kind of idea called CADE, classifier adjusted density estimation for anomaly detection and one class classification. Pretty fun. What this does, it says, okay, you have your data set. And what we're going to do is we're going to keep track of your original data. And we're going to give these the label zeros. And the data is kind of distributed in your feature space, and maybe you have some outliers in there as well. And then we're going to add a whole bunch of synthetically generated data elements that we just uniformly sample from the feature space. Numerically, that's easy, again, for categorical features, but you could kind of uniformly sample based on the distribution that the levels occur with and so on. So, okay, fine. We also sample a whole bunch uniformly. We cover basically this map with synthetic instances. And we will all give these the label 1. And then we pick our favorite classification technique, which we know is CatBoost or XGBoost or Random Forest or LightGBM. And we just say, well, learn whether something was a synthetic example or something was a real example. For areas where most of the real examples showed up in, it's not going to do a good job there. Right? It's going to make a lot of mistakes. It's basically going to say, well, here it's 50-50, I guess. Right? For areas where your data is less dense, and so where maybe you have a couple of anomalies there, but not a lot, it will probably be more oriented to say, here is an area with a lot of synthetic examples. And yes, it will make a mistake for our instance and saying, well, here, it's not like 50% like the others. Here, I think you're 70% likely to be a synthetic example. We don't care so much about the fact that the model is wrong in this case. We directly then utilize this probability to say, well, or anomalies. Right? So you basically just generate synthetic data, you throw XGBoost on top of it, and you use that to directly predict you how synthetic something looks. Right? Very easy idea. Okay, that's it for unsupervised learning. We have data science tools coming up next, but to leave at a kind of clean state, I suggest that we start then with that chapter next week. See you all next week.